So now a brief glance into the sessions. So the first session, as Mayank has already pointed out, it would be on responsible AI, specifically geared towards fairness and interpretability. The second session today, in the second half of the day, will be about machine learning and its uses in NLP. The third session, that is the day 2, session 1, that is again primarily geared towards machine learning in NLP. The fourth session is machine learning applications beyond CS. This is again going to be an exciting session where we are going to have glimpses of how machine learning is being used in urban sciences, art sciences, health, informatics, and biomedicine. So the third day, first session is again ML applications beyond CS. Once again, we are going to listen to talks like uses of ML in art system sciences, uses of ML in modeling monsoon characteristics, in using artificial intelligence for pandemic responses. And then finally, we will have the winners of the datathon, Indoari and multilingual abusive content comment detection, results declared by Jayesh. On the third day, session 2, we will have talks from different areas, but predominantly in the area of ethics and trustworthy natural language models. And we will finish with the conclusion and vote of thanks. So we were wondering whether we have been able to be true to the theme of the workshop, and I looked into the tag cloud of the different abstracts sent by our speakers, and it indeed seems that data is the central part of all the abstracts that we have received. So I think we are very much in line with the spirit of the workshop, and therefore, without any further ado, let us light the lamp and begin IndoML 2021. Okay, I think that's enough. So over to you, Mayank.
Yeah, thanks very much. So it is a pleasure to introduce our first speaker, Dr. Sharad Goel. So Dr. Sharad Goel is a professor of public policy at Harvard Kennedy School, and he recently worked on several problems like policing practices, including statistical tests for discrimination, fair machine learning, including in automated speech recognition and democratic governance, including swing voting, polling errors, voter fraud, and political polarization. So today he will be talking about designing equitable algorithms for criminal justice and beyond. Yes, over to you, Dr. Sharad.
Hi, thanks for that introduction, and thanks for the invitation to join you all today. Can everyone see my screen?
Yes, yes. Yeah.
Great. Okay, so today I'll talk a bit about designing equitable algorithms based on experience that my group has had over the last several years, and I'll be focusing a little bit on criminal justice applications, but many of the principles really extend beyond into a variety of applications. So I want to start with this case study of racial disparities in automated speech recognition. So as we all know, we now have powerful speech-to-text systems in our pockets, in our phones. They're widely used as virtual assistants, Siri, Alexa, Google Assistant, for dictation, translation, subtitling, hands-free computing. And these aren't just a nice thing to have. They're really an essential part of life for many folks, especially people with physical disparities. But with many technologies, many emerging technologies, there's worries that they don't perform equally well across for everybody in the population. And so we audited 5 of the leading ASR, automated speech recognition providers, from Amazon, Apple, Google, IBM, and Microsoft by comparing human and machine-generated transcripts for 20 hours of audio of black and white speakers. And so we took all this audio, we had humans transcribe it, and so we knew what the ground truth answers were, what the best transcription was from this audio. We ran all these things through the ASR providers, and then we just compared the error rates from the results that were returned. And what we found was pretty striking. This is a plot of error rates on the vertical axis, and then the different providers on the x-axis. And what we see here is this quite large gap between white speakers and black speakers on these word error rates, so almost a 2x gap across speakers. So even though there's quite a lot of heterogeneity across the quality of these different services, in almost all these cases, we're seeing about a 2x gap in error rates. And so quite a large relative and absolute gap in performance. Now, what's interesting is that even on a subset of identical phrases spoken by the black and white speakers in our data set, error rates were still about twice as large for black speakers. And so this really points to the acoustic models themselves as one of the sources of creating these disparities. So if you know a little bit about how these automated speech recognition models work, there are really 2 components. There's the acoustic model, and then there's the language model that's looking at grammar. And we're really seeing, what we're finding is that these language models perform comparably, but it's the acoustic models that are really creating these disparities. So even when the exact same phrases are spoken by black and white speakers, we're seeing about this 2x gap in errors with worse performance for black speakers. So what do you do with this type of finding? I think there are a variety of immediate interventions. I mean, the first and arguably the most obvious is to collect more training data, more diverse training data, both of what's called AV speech, African American Vernacular English. This is a term that linguists often use to describe the variety of English that many black speakers use in the United States, but also a variety of other styles of English. And one of the reasons I got started on this project is that for many years, when my parents would leave messages for me on the phone and these would get automatically transcribed, they really came out as being nonsensical, and the speech recognition services really weren't appropriate for people who weren't speaking what's quote unquote standard English. So it really it points to this value of collecting more diverse training data. The second is simply to invest more resources broadly into ASR systems, and including the institutions that build them, to ensure that that these ecosystems are more inclusive. So you can imagine that if we had greater representation among the types of people who are building and using these systems, then these types of disparities would be more quickly recognized, and arguably these products would be improved before they were actually released into the wild. The third is assessing and regularly reporting on progress over time. We were able to do this work, but it was a fair amount of logistical challenges that we encountered, and it was certainly difficult for us to do this from the outside. And so having this type of internal auditing, regular reporting would be quite useful. And then finally, learning from the types of legislative progress that have been made in other domains, for example, computer vision, where we might have more oversight and higher standards for deploying these types of technologies into the wild. So if you want to read more about this particular example, please check out our paper that we released last year, that we published last year in PNAS. So now with this example in mind, I want to talk more broadly about the dominant ways of understanding fairness, particularly in the machine learning and the computer science community. And what I'll offer is a critique of what I call deontological approaches to fairness. I'll define this term deontological in a minute. But this is, one way that I think of many of the approaches that are now becoming popularized in the computer science community. And in response to these deontological approaches, afterward, I will present an alternative consequentialist approach to fairness, which I think can help us mitigate some of the limitations of this dominant approach. Okay, so in much of the material that I'll talk about in this part of the presentation is drawn from this paper with Sam Corbett-Davies, The Measure and Mismeasure of Fairness. So, as many of you likely know, many high-stakes decisions are made by first estimating either statistically or just intuitively estimating the likelihood of some adverse outcome based on the available information. So in lending, we might estimate the risk of default using credit scores. Incarceration, in many cases, is based on the risk of recidivism, the risk of future offense. And the idea is that decisions that are guided by statistical risk assessments, in theory, can be more equitable, they can be more consistent than those made by intuition and expertise alone. But at the same time, there's a lot of worry that these types of tools can embed bias themselves. So even though there's this potential benefit of limiting bias from unaided human decisions, there's a real concern that bias itself will creep in to these decisions by automating them. Now, what do I mean by deontological ethics? So here, this is this idea, not only in the algorithmic world, but kind of much more broadly, it's this idea that the morality of an action is judged based on whether that action itself is inherently right or wrong under some normative set of rules, rather than the consequences that stem from that action. So I might say that this, I'll give you many examples of this in a minute, but I can say that there's a certain way of doing things. There's a process by which we do something. These are the rules that I'm laying out, and if we deviate from those rules, then that itself makes that action inherently wrong, even if the outcome, the consequences of that action in some sense are legitimate. The way that I did that, or the reason I'm doing this itself could be deemed morally wrong. So this is what I mean by deontological ethics, and I'm going to connect that idea to this algorithmic framework. Okay, so one of the dominant approaches to the dominant mathematical approaches to fairness is what I call classification parity. And so here the idea is that an algorithm is considered to be fair if error rates are approximately equal across demographic groups. And for simplicity, I'm gonna take this kind of somewhat reductionist, this simplistic view of talking about two race groups, white and black individuals, in particular race groups that are salient to the United States. And again, the idea here is that an algorithm is considered fair. The rule is that the algorithm is fair if error rates are approximately equal across these groups. And again, this makes a lot of sense. And we saw in this motivating example that I started with automated speech recognition, that here we saw these big gaps in error rates across groups, and that I think to many people feels like it's inherently problematic. And so this is part of where this intuition is coming from when we're demanding this classification parity. So this isn't only something that has been adopted in the computer science community. It's really something that has gained traction in public policy circles as well. And so this is some legislation that was proposed in the United States a couple years ago in the context of what's called pretrial risk assessment. So after someone is arrested in the United States, a judge has to make this high stakes decision about whether or not to detain or release that individual pending further court proceedings. And so this is what's called a pretrial risk assessment. The person hasn't been put on trial yet, but is pretrial, and there's this decision made about whether or not this individual is sufficiently safe to be released into the community. And so this legislation was designed to ensure that these risk assessments, these algorithmic risk assessments, were indeed equitable, were fair, and this is the language that I'm going to read from now from that proposed legislation. Pretrial risk assessment algorithms shall not be used by the state until first shown to be free of bias, meaning that an algorithm has been formally tested and the rate of error is balanced as between protected classes and those not in protected classes. So again, this very, very simple, intuitive idea that fairness, the rule for fairness, is that the error rate is balanced or approximately equal across groups. It's a very simple idea. Now, what I'm going to argue is that even though this idea, this deontological idea, this rule for fairness makes a lot of sense, or it feels like it makes a lot of sense, in fact, it's there's quite a bit of subtlety in this idea. Okay, so what do we mean by error rate? There are many, many ways of formalizing error rates. I'm going to take one particularly common approach, and this is what's called a false positive rate. And to be super concrete, I'm going to phrase the definition of the false positive rate in terms of this pretrial risk assessment application. So what does it mean here? It means among people who ultimately did not go on to reoffend. Remember, the risk assessment is designed to help us identify those who do go on to reoffend, their risk of recidivating, their risk of reoffending. So here the false positive rate says among people who do not ultimately go on to reoffend, what proportion were deemed high risk by the algorithm. So these were false positives. Even though they were not positives in reality, they did not go on to reoffend, they were tagged as positives falsely by the algorithm. So this is our false positive rate. Okay, so now a study in the United States a few years ago looked at the use of one particularly popular algorithm for these pretrial risk assessments, and looked at the different error rates that this algorithm was leading to in two different populations of Black individuals and white individuals in Broward County, specific jurisdiction in the United States. And what they found was pretty striking. They found that among Black defendants who did not go on to reoffend, about a third, 31%, were deemed high risk by the algorithm. And among white defendants who did not go on to reoffend, about 15% were deemed high risk by the algorithm. So this is a pretty big gap. It was a gap of 15 percentage points, so in absolute terms, about a 2x gap in relative terms. So quite a big gap, both in absolute and in relative terms. So this is the gap again in the false positive rates. And again, you look at this and you're like, intuitively, this feels really bad. It feels like something has gone fundamentally wrong, in that maybe somebody messed up when they were designing this algorithm. And that was the first thought that I had too when I saw this example. I was like, oh, okay, well, clearly we can do better, that we need to work harder, and we can design a more equitable algorithm. And now what I'm going to argue again is, in fact, there's something more subtle happening here, in that this gap in error rates doesn't necessarily mean what we first think it means. So I'm going to do this in pictures. So we imagine we have these two groups. We have the blue group and we have the orange group. And there are a couple of features of this diagram that I want to point out. So the first is that underneath each of these stick figures, I have these numbers corresponding to the estimated risk of recidivism, the risk of reoffending. So I have these low risk individuals here on the left, so 10, 20% chance of reoffending. These high risk people on the right, 50, 70%, 80, 90% chance of reoffending. I'm going to assume that in fact all of these risks are perfect estimates of risk given the available information. So there's no statistical estimation error in these things. We're just going to assume that all of this is perfect. I'm going to still demonstrate that there's some kind of subtle issues here that cause us to more carefully try to understand what these error rates mean. So in the absence of statistical error, we still have these very complicated questions of interpreting error rates. So we have these error rates for each individual. Because we have these two different groups, anytime I split my population into groups that are non-random, I can expect there to be distributional differences. And so here what we see is this orange group is higher risk than this blue group. This isn't saying anything inherent. This isn't saying that the blue group is inherently less risky than the orange group, but really this might be a product of different covariate distributions in these different groups, and that is what's driving this different observed distributions of risk. So I have these different distributions of risk in these two groups. And now finally, I have this line that I've drawn here that separates what I'm going to call the quote unquote high risk individuals from the low risk individuals. So we have these, so I have to partition. If I'm going to make a binary classification of saying high risk and low risk, I have to pick some threshold for making that classification. And here I've somewhat arbitrarily just picked 50%, but I could draw this anywhere, but here I've drawn it at 50%, and I'm going to call these people high risk and these people low risk. And importantly, I'm drawing a single threshold. So I'm making this decision on whether or not someone is categorized as high risk or low risk only based on their risk itself, not based on group membership. And so I'm applying the exact same standard to everybody. And arguably, this is an equitable way to classify folks. If I give you their risk, and I say these are perfect estimates of risk given the available information, now I'm going to classify you only based on that risk score. Arguably, that is one intuitively fair, equitable way of making that classification. So now let's see what happens when I dive into this example. Let's look at this blue group. Now remember, what is my definition of false positive rate? Among people who do not go on to reoffend, the proportion that are deemed high risk. So now I'm highlighting these people that kind of randomly went on to reoffend. So 5 people randomly went on to reoffend. That means 8 people in this simple example did not go on to reoffend. Those are the ones marked in blue. Of those 8 people who did not go on to reoffend, 2 of them are to the right of this dashed line, and those are the people who are deemed high risk. And so in this case, I just have 2 over 8, or 25% false positive rate. And so about a quarter false positive rate in this example. So now, just mechanically, I'm going to look at this orange group. So orange group, remember, is a higher risk group. The distribution of risk is shifted to the right in this example. So now I have, this is a higher risk group. On average, more people will reoffend. That means that fewer people will not reoffend. That means that the denominator of this on this example will be smaller. And now the way that I have drawn this picture, among those people who do not go on to reoffend, a higher proportion will be deemed high risk. And so here I have this 42% false positive rate. And so again, this is just kind of mechanical. I have these 2 different distributions of risk, this lower risk group in blue, this higher risk group in orange. And in large part, because of this different distribution of risk in these 2 different groups, I have these differences in false positive rates. And so here, even though I apply the exact same standard, I have this difference in false positive rates. So now, again, that was just kind of a stylized example showing how these differences in false positive rates can arise even when we arguably are making an equitable classification decision based on the available information. Now let's look at the real data. In the real data, we don't know exactly what everyone's risk is. That's not something that we can easily, or that's not something we can definitively answer. But what we can do is estimate the risk based on the observed information. And so here again, these are estimates of the risk distribution across these 2 different groups. So this corresponds to the stylized example that I was talking about. And what we see here is that this red group, in fact, it does have a very different risk distribution and a higher base rate, a heavier tail than the blue group. And what this example, this stylized example shows is that when I have these differences in base rates, when I have these differences in risk distributions, I can generically expect to have differences in error rates themselves. And so this example is highlighting this idea that differences in error rates are what we expect when we have differences in risk distributions, and in many cases we expect differences in risk distributions. Okay, so this phenomenon is related to what economists called inframarginal statistics. And so what is this idea? This means that a statistic is inframarginal if it depends, and here what I mean by statistic is something like a false positive rate. Every kind of summary statistic of error that we can think of is inframarginal in the sense that I'll describe now, in that the statistic depends not only on our threshold for classifying people as high risk or low risk, but it also depends on the distribution of risk. So even though we have this normative idea of risk depending on applying the same standard to everybody based on that risk score, these inframarginal statistics like false positive rates and like really any other error rate statistic that we can think of doesn't just capture what's happening at the margin, at the threshold. It really depends on what's going on with the entire distribution. And so now you might think at this point, okay, I understand mechanically when I have differences in risk distributions, then things will just be different. I expect to see different error rates. But why? But that is itself problematic. It's even though I have these, just because I expect to have differences in error rates doesn't mean I should be happy with these differences in error rates. And it still might mean that these groups with higher error rates are being disadvantaged in some sense. So now what I'm going to show is a very simple example that even pushes back against that quite reasonable intuition. So remember, here's my orange group, this higher risk group, and this was the 42% false positive rate group. And now, how can I lower the risk in this group, there's false positive rate in this group? Well, I can go out and arrest a bunch of college protesters. So of course I'm being facetious here. We're not going to actually go out and arrest a bunch of college protesters, but the point here is if I were to do this, what's going to happen? The algorithm correctly identifies that these college protesters are in fact low risk. It classifies them as low risk. Now, most of those low risk individuals are going to end up in the denominator. And now all of a sudden I have this relatively low false positive rate. So I went from this situation where I'm seeing this high false positive rate in the orange group relative to the blue group, and might say, okay, well, I'm burdening this orange group with this high false positive rate, to this situation where my false positive rates are equal, my error rates are equal, but clearly I made the orange group worse off by doing this. I burdened that orange group more, even though if I just looked at these summary statistics, I would say, oh, things are actually not so bad now between these two groups. So the point, again, isn't that I'm worried about incentives. I'm not worried that if I say design my algorithm to equalize false positive rates, I'm going to encourage people to go out and make this orange group worse off. But the point here is that if you don't consider the distribution of risk, it's very hard to interpret what these error rates really mean. Now, what is the difference here? I mean, we in the machine learning community, we use these error rates all the time. This is kind of the bread and butter of evaluating and developing new approaches. And so is this how does this discussion that we've been having, how does this relate to our kind of normal state of affairs? Now, here, what I'm arguing is that in traditional machine learning settings, in the settings where we're familiar, what is our usual mode of operation? We compare multiple models on the same data set. And so we say, here are my 5 benchmark state-of-the-art models. I'm going to introduce a new model. I'm going to take some test data set. I'm going to run all my models on that test data set and see which performs the best. That's sort of our standard machine learning pipeline. But this approach, this fair machine learning approach that I just discussed, here the idea is effectively we have one model, one risk assessment tool, but we're evaluating it on multiple data sets. And so here we took our one model and we said, let's look at the performance of that one model on two different subpopulations in my larger population. And now let's compare error rates on those two subpopulations. So that is a pretty difficult thing to compare. So this is really an apples to oranges comparison. Relative to what we're normally used to in machine learning, where we're saying we have multiple models that we're comparing, but on the same data set. So it's similar, but very different in a way that makes it hard to interpret the results. Now, in some settings, these differences in error rates across groups can actually be a strong indicator of algorithmic problems. And so going back to this automated speech recognition example that we started with, unlike pretrial risk assessments, we have pretty strong reason to believe that with more data, with possibly better models, there shouldn't be a difference in error rates across different types of speech that we encounter. So it's not that the type of English that's spoken commonly by white Americans is different than the type of English that's commonly spoken by Black Americans. There's nothing kind of inherently more difficult for automated speech recognition to transcribe speech from these two different subpopulations, and so we would expect the error rates to be comparable, which is very different from the situation that we have in many of these risk assessment algorithms, where there we generically do expect base rates to be different. And when you expect when base rates are different, that suggests that the difficulty of the problem, the statistical difficulty of the problem, is in fact is quite a bit different as well. And so there we expect differences in performance, differences in error rates. Okay, so this was just a sort of brief critique of the style of reasoning, this deontological mode of reasoning that has become popular in the machine learning community, where we say what our rules are, for example, demanding parity and error rates, and then we evaluate our algorithms relative to those rules. So, I've tried to argue that things can go quite wrong when we take that approach. And so now I want to present an alternative, what I call a consequentialist approach to fairness. And so here I want to give a slightly different motivating example. So in many jurisdictions, especially in the United States, people can be jailed for failing to appear in mandatory court appointments. And so as a result, it's possible to reduce this type of incarceration by helping people appear in court. And so one way to do this is to provide folks with free door-to-door rideshare service. So one of the big barriers to getting to court is transportation. So people don't always live close to the courthouse. There's not necessarily good public transportation, and they're not easy ways to make it to court. And so one alternative, or one possibility to support this type of court appearance, is providing people with rides to get to court. Now, of course, it would be better to just not jail people for these types of, I would say, minor infractions, but that's harder from a policy perspective. And so really I'm gonna focus on this question of how do you equitably provide this type of rideshare service to folks who have upcoming court dates. So imagine we have some pool of money, $100,000, to purchase rides for people with upcoming court dates. And the question is, who should we give rides to? So this is actually, it's not a hypothetical. We're preparing to give out rides next year in California, and we're up against this problem of how do we decide who to give these rides to? So one pretty natural approach to this problem is to simply allocate the rides in a way that maximizes the number of people who make it to court. And so conceptually, this is straightforward. Statistically, it's hard, but conceptually, it's pretty straightforward. We estimate the heterogeneous treatment effect. And so we say, how likely is it what is the extra boost, the extra chance that someone is going to go to court if I give them a ride? I can estimate that maybe through a randomized controlled experiment, but there's some way I can estimate that. And now I just rank people and allocate by the estimated effect per dollar. So some people live further from the courthouse, and so it might cost me more to provide that ride, but they might also have a large effect. And so I just look at what's that boost I can get by giving them a ride, divided by the cost of providing that ride. Now I have an effect per dollar, and I can just rank people by this estimated effect per dollar, and then allocate from the top of the list down until I run out of my budget. So this is a very natural approach to maximize the number of people who make it to court. Okay, so now what can go wrong? So here's a picture of a particular county in California where we're planning to roll out this service, and these dots here represent the demographic of the individuals by their race. And what we see in this particular county, and this is very kind of broadly similar to what we see in many parts of the United States, is a lot of segregation. And so we see that the colors represent that demographic group defined by race or ethnicity, and what we see is a lot of segregation. And in particular, what we see is that the people who are going to be most expensive for providing these rides for getting to the courthouse tend to be of Asian descent. They live on the outskirts of the city. The courthouse is right around here. The outskirts of the county is here, and these folks are going to be much more expensive to provide rides to than the people who are a bit closer to the courthouse, which are a different demographic than the people who live on the outer edges of the county. And so if we were to take this this optimization approach, then we're likely to disadvantage this non-representative set of people who live out on the fringes of the county. Okay, so this introduces this tension. And there are a couple ways that we can deal with this tension. So the first is this deontological approach that I started out the talk with, where we might demand an equal proportion of people receive rides in groups defined by race or other characteristics. That's one approach that we can take. And if we do that, we have this trade-off. So here, these are hypothetical numbers, but I think they hopefully make the point that we might say, well, first we can just optimize. We can forget about all of these equity considerations. We can optimize for the most number of people getting to court, and we might have something like 1,000 new appearances, and 30% of one group gets rides, and 20% of another group gets rides. And so we have this disparity in who's getting the rides, but we get the most number of people to court. Now, an alternative is, say, if we demand equal allocation, we might get 800 new appearances, so fewer new appearances, but 20% of people in each group gets a ride. So we're able to balance the number of people or the proportion of people from each group that gets a ride, but we have fewer. The cost of that balancing is that a fewer number of overall people will make it to court overall, and so we have this tension. And so this traditional deontological approach, this rule that says I need to have the same number of people make it, or the same proportion of people make it to court from each of these groups, ignores the outcomes, the consequences of that mode of reasoning, of that type of policy decision. And so in general, we can expect, if we're ignoring the consequences, then the algorithms that we develop are going to be misaligned with our true preferences are as policymakers. And so here, this approach, this consequentialist approach, is to aim for decisions that maximize stakeholder utility, including one's preferences for parity, but are really directly optimizing for the outcomes that we care about, rather than laying out these rules ahead of time and then hoping for the best. So again, let me just sort of, I can simplistically think that we have this spectrum of, on one side, optimizing for appearances, on the other side, optimizing for equal allocation across groups, and my real preferences might lie somewhere in the middle. And so now this introduces this trade-off. Here I can say the number of additional people that appears on one axis, the percent of people in some target group that receives transportation benefits is on the other axis. all of these points are points that are feasible given my budget, I can say, okay, I can create policies of handing out my budget in ways that gets me to any of these points in this gray area. And so I can realize this point in red. If you want this point, I can give you this point. In reality, you wouldn't want this point. You would rather be on this frontier here. And so this is the Pareto frontier that's being sketched out. It says this point dominates this point. So I get more people with still maintaining the proportion of people in the target group who receive benefits. I can still get more people overall by selecting this point. These points here, I might want them, but they're out of budget, so I'm really restricted to points that lie on this curve. And so now I can say, well, which of these points on this curve should I pick? One option is that I just maximize for appearances. This, again, this straightforward, naive optimization approach of saying, let's forget about equity considerations, let's maximize for appearances. Another approach is, again, this deontological approach of, let's say, I just want demographic parity. And so this is going to place me somewhere else on this curve. Ahead of time, I won't know where I'm going to fall on this curve. If I just say my rule is demographic parity, I won't know where I'm going to lie, but I'll lie somewhere on that curve. But then really what I might care about is maximizing my utility. And so here, again, the idea is I want to balance, I want to explicitly balance this trade-off, that my desire to maximize the number of people that make it to court, and also ensure that these are equitable. And so here I might choose a point that's somewhere in between. And this idea of this consequentialist approach to fairness is simply saying, let's be explicit about the trade-offs and then select that point with these trade-offs in mind, rather than putting the rules first and then hoping for the best. Okay, so summarizing here, that this deontological approach, we force our decisions to satisfy particular mathematical fairness constraints, for example, demographic parity. It can and typically will result in suboptimal outcomes if we're not cognizant of the downstream consequences of those types of constraints. So here, very quickly, in reality, so I sketched this general idea of how we might think about designing fair algorithms. In reality, we have to learn these policies from data. I'm not going to go in that now, but I'll say that this is a variant in practice. What we're doing here is a variant of contextual bandit algorithms. And if you're interested in reading more about that, you can check out our paper on learning to be fair. So just in the interest of time, I'm going to skip this last part, and I want to wrap up by summarizing. So many popular algorithms, for example, automated speech recognition, exhibit troubling disparities. Past attempts to address these inequities have focused on these deontological approaches, these rules for requiring error rate parity, like requiring error rate parity, but they can exacerbate problems if we're not careful. And so an alternative is this consequentialist approach to directly consider the trade-offs that are inherent to policy decisions. So thanks everybody for listening to this presentation. I'm happy to take questions.
Thanks, Sarath. So yeah, we have one question from the audience, but I will first of all request if there are any questions from the panelists.
Hi, Sharad. Animesh here. So
Hi.
It was a great talk. So I was more keen on the first part of the talk that you described about the discrepancies and the disparities in the speech recognition systems. So that was kind of interesting. Like it reminded me of the gender shades paper. So where they were looking into image recognitions and cafe recognition and face recognition softwares. So recently, like what we kind of saw is that if you have adversarial attacks to these kind of images, actually the disparities are even larger. So I was wondering, like, since ASR systems are typically noisy, so, and if they're like made to work in, say, some supermarkets, malls, so noise is kind of inevitable. So do you think that in a similar way as we have seen, so this work is going to come up in ICWSM 22, will this disparity be more pronounced? Like, what would be your take on that?
Yeah, I mean, I think it's definitely possible. I mean, and also to make this connection, I'm glad you brought up this gender shapes work. That was definitely one of the inspirations for the work that we were doing here, in one of the most prominent examples of these disparities in performance across these types of models. And so I haven't looked at the performance of these in these noisy environments, but I think it's very possible that the disparities become even more pronounced in less than ideal settings.
Thank you.
Yeah, thanks, Professor Anmesh. Yes, so we have one question from Aman, and the question is this, that in the illustrative example for the pre-trial risk assessment, why is FPR a useful metric to look at and not something like precision, given the likely imbalance between the high and the low risk individuals? And does the analysis gets affected by this choice?
Oh yeah, so precision. So yeah, it's a good question. So in fact, the argument that I presented applies more or less unchanged for everything you can compute from a confusion matrix. So including precision, recall, true positive rate, false positive rate, even AUC, all of these metrics of error, they all apply this idea of inframarginality. It applies equally to all of these different measures.
Okay. Yeah, thanks, sir. Yeah, one more question. So there are 3 questions by Ajay. Maybe I will ask them one by one. So the first question is, history of group decide the future of the group. How fair it is?
Maybe I'm not quite sure I followed the...
Exactly. Yeah. So even I'm not very sure about this. So maybe we can then move to the next one. One or multiple models. What model is trained on biased data, and do we expect fairness? Not very sure about this either. For ASR overlap speech, more than 2 speakers are talking at same time. How to address this, and few or many good data sets you point to?
Yeah, so I mean, for this last thing, I think we, again, in this situation of less than ideal settings, when these are harder transcription tasks, I think it's quite plausible that we see differences, even larger disparities in error rates. And so, we're already seeing these 2x gaps in error rates, and we can go to these natural, even more real world settings, then we might expect to see these gaps to become even larger.
Okay. So that's all questions that we have from our side. Yeah, thanks, Sharath, and thanks for accepting our invite. Thank you.
Thanks. Yeah, thanks for the invitation, and I'm really happy to participate in this.
Yeah, thank you very much. Yes, so our next speaker is Dr. Samir Singh. So Dr. Samir Singh is an associate professor of computer science at University of California, Irvine, and an Allen AI fellow at Allen Institute of AI. He is working primarily on robustness and interpretability of machine learning algorithms, along with the models that reason with text and structure for NLP. Samir was a postdoctoral researcher at University of Washington and received his PhD from University of Massachusetts. He has received the NSF Career Award, selected as a DARPA Riser, UCI Distinguished Early Career Faculty Award, and Hellman Faculty Fellowship. His group has received funding from Allen Institute of AI, Amazon, NSF, DARPA, Adobe Research, Hasso Plattner Institute, NEC, Base 11, and FICO. Samir has published extensively at machine learning and NLP venues and received conference paper awards at KDD 16, ACL 2018, AMNLP 2019, AKBC 2020, and ACL 2020. So today he will be talking about evaluating and testing natural language processing models. Yeah, over to you, Samir.
Thank you. And I assume you can hear me fine?
Yes.
Awesome. Thank you. So today I'm going to be talking about evaluating and testing NLP models, and a lot of what I'm going to talk about goes beyond just NLP. So hopefully people who are experts in other domains can take some of these ideas and think about what it means for what they work on. Okay. So let me give you sort of a introduction to where NLP is and why I wanted to work in this specific area. Right. So think about this problem of working with a model and trying to figure out whether it really works or not, right? So suppose you're a researcher, you're working on your computer, and you have a nice model that you're pretty happy with. You've been training it, taking care of it, growing it, and you like it a lot. And then suddenly a new model comes out. Everybody's tweeting about this. Everybody says that's the new best thing, called Oscar in this case. And that's just supposed to be better than what you're supposed to be doing. And so the natural question that comes up is this Oscar thing any better than my existing model, right? Like, is there anything more interesting in this model than what I have already, right? And Facebook, all of these places are also looking at these new models coming out and asking, hey, should we replace whatever we're using right now, underlying our NLP model, with this new thing that has come out, right? So let's actually think about how it is evaluated right now, this question of how models really work. One popular way is to pick a task and just measure accuracy on the task, right? So let's say we pick question answering and we say like, okay, if this model is good, if it comes close to humans, then it must be good. And so that was the idea with one of the most popular leaderboards for this task called Squad. This is Stanford question answering dataset. It came out in 2016, and it took about 3 or 3.5 years to essentially get a model to be better than humans on that task, right? Which kind of makes the leaderboard a little less useful, because you have something that's better than humans, it's not worth competing on that task. Right? They came up with a different leaderboard called Squad 2.0, and you can see in this Squad 2.0 as well. It came out in 2018 sometime. By 2019, it took an year and a half. The models were better than humans again. Okay. So maybe question answering, at least the way these guys phrased it, maybe that's not the right thing to be measuring your performance on. If you want to see how good you should be looking at the performance, maybe you should be looking at the performance on a bunch of different tasks. That was the idea behind the Glue leaderboard, which contained many, many different tasks. So you can see certainly this screen is full of numbers. That's because there are lots of tasks, which are columns here, where the models are being evaluated on. And you can see in the ranked list here, humans are at number 9. And this is a pretty old screenshot. Humans are much worse on this task. So again, it kind of loses its purpose. Like the models are competing on being better than humans. It's kind of meaningless at that point. They had a sequel called Super Glue, which had a bunch of even more difficult tasks. And it took a little bit longer, but even on that leaderboard, I think earlier this year, it's been almost a year, I think, the numbers are now better than humans again. And this is a pretty old screenshot, but the humans are at number 3. And all these other models seem to be better at that. So one conclusion after looking at all of these things is, why do we need these new models? Why do we need to be trying to get better at NLP? It's pretty clear we should just be patting ourselves on the back and congratulate ourselves because we have solved NLP. Now, if you followed machine learning and if you know what I work on, these are the kind of questions that this is clearly not the case, right? We are far from solving NLP. There are lots of problems with these models. I'm going to give you a few examples of some of them. The first one is that there are lots of shortcuts in these models where it gets the things right for completely wrong reasons. So here's a quick example where there's an image and a question being asked of the image. So there's NLP, but there's also vision going on here. What is the mustache made of? The model is supposed to look at that question, understand what's going on here, understand that mustaches are this conceptual thing here, doesn't necessarily mean hair. In this case, it's banana, and it's able to give the answer banana, even though it has never seen such a mustache, and I'm sure most of you have never seen such a mustache in real world. And this seems really cool. The model is able to answer it. That's why it's better than humans. It's really accurate. And so, yeah, I think this is cool. What's the problem? The problem is if you ask it a different question, what are the eyes made of? The model says bananas. Again, this is really weird because we have completely changed the question. The answer is clearly not bananas, but the model seems to be saying the same thing. You can say what is, and it says banana. You can say what, and it says banana. Somehow it's focusing on pretty much any question that is asking about what's the object in this image. It seems to be saying banana, and it looks accurate because the benchmark doesn't somehow ask these different questions. They only ask the first question. Right? Here's another example. This one is a little bit more realistic and maybe a little bit more dangerous in some sense. This is sensitivity to phrasing. So you could have another image. This is a little bit more realistic. You're walking around in a foreign country and you see a stop sign, and let's assume you don't know what that means. You can say, hey, what type of road sign is shown? You can take a photo and the model is able to say stop and everything's great, right? But it turns out that instead of what type of road sign is shown, if you instead say which type of road sign is shown, which is essentially the same question. These two questions should give you the same answer. Turns out the model says, do not enter. It's the same question you're asking it slightly differently. It has changed its answer. Here's another example. This is an example of question answering from a piece of text. So the kind of thing you would do web search over. So, for example, you might want to know how long is the Rhine River? And these question answering systems look at the paragraphs, figure out, okay, this information is kind of spread out over multiple sentences, but they're able to figure out that 1230 kilometers is how long Rhine is. But if you ask a slightly different question, which is essentially the same question, except that you add an extra question mark. It's not even a typo. It's just you really, really care about the answer. There's no reason for the model to give a different answer, but it does. It says more than 1 million. And so clearly there is a mismatch here. These models are not the complete solution for sure, but the leaderboards seem to suggest that they are, right? So what's kind of going on here? Essentially, I think there's a lot of problem with these accuracy and leaderboards where things look very different from what they actually are. One of the biggest problems is that the leaderboards essentially duplicate the biases. If there is a shortcut in the training data, it shows up in your test data as well. And it kind of does not represent real world usage. This is one of the fundamental problems where a lot of these issues come up. But there's also sort of a bigger fundamental issue with leaderboards, which is that they essentially compute a single number and summarize everything with a single number, and a bigger number is better and lower number is worse. But that's really, really insufficient because that single number by itself doesn't mean much. It's more about the difficulty of the data rather than the model. But something that we're going to focus on a lot in this talk is that it does not break down the model capabilities. It does not tell us what the model is good at. It does not tell us what the model is bad at. How can we improve the model? None of this stuff. Right? And so if we go back to this question of figuring out, does a model really work? Should I replace my model with this new thing? Should I use this new thing in our products? We know that relying on leaderboards and accuracy is not the right answer. And in other words, that this very fundamental problem, very common problem, is not actually a solved problem. We don't really know how to evaluate these models. And so in this talk, I'm going to be talking about some line of research that we've been doing in thinking about what are the possible bugs. And some of these ideas will go beyond NLP, as we will see. And in some sense, I don't care whether we're going to be doing this automatically or manually. So we're going to be looking at approaches that do both versions. There are ones that try to automatically find bugs and sort of almost like in an adversarial way. But we also have ways to help you manually find bugs. Yeah. Behind all of the methods I'm going to talk about is this idea of perturbation-based testing, where you have your original data, and you're not going to rely just on the performance on the original data, but you're going to make some changes to it. Right? So you can think of some transformation that you're going to do to the original x and y to form these x and prime and y prime pairs. And this transformation is very specific, very designed. You're not just making random perturbations. This is a very sort of domain specific, NLP specific kind of transformation. And you're going to have these changes and you're going to have some expected y prime, right? So y prime is like, hey, I've made a change such that y should be different. So it's y prime. And then you're just going to run x through the model, see what comes out of the model, see if these two things match or not. This is a very high level description. We're going to cover a bunch of things within this sort of bigger umbrella. We're going to cover a bunch of automated techniques. I'm going to cover two, but there are a bunch of other ones as well, where you automatically try to find the transformations, essentially, or the transformation function that gives you mismatches. That's what seals and triggers does. And then you can also think about manually creating transformation functions just to create robust evaluation benchmarks. Right? And there's a bunch of work we've done. I'm going to only talk about one of them. And for the most part, I'm going to cover the rest of them very quickly and focus on checklist, which was our paper last year, on how to test NLP models. Okay, so first I'm going to start with this work led by Eric Wallace called Triggers, where the idea was we wanted to learn a transformation function that identifies an X. So we're going to concatenate an irrelevant phrase to X, and we expect the output not to change, but we're going to find the phrase that actually causes the model prediction to change a lot. All right, so y prime is we expect it to be the same as y, and so that's what it's going to look like. I have to warn you that we were trying to find the phrase that can make the model misbehave as much as possible. And so that means that this is going to have some strong language. We wanted to find the worst possible bug, so to say. Okay. So in this work, here's kind of what happens with these triggers. These triggers are these short phrases that don't mean anything. So you can see the trigger here is zoning tapping fairness. That doesn't really mean much. And you have a bunch of inputs here that are all positive reviews, you know, movies amazing, give him the Oscar, worth every minute, and so on. And the model is correct on them. The model predicts positive for each of these movies. But when you add this trigger as a prefix to these negative, you can see positive going to negative. In fact, the accuracy of the model being as high as 86% drops to 29% because almost all of the positive reviews become negative. It's just one example, but this is what it is. Here's a slightly scarier example. This is for question answering. This is a pretty accurate model, pretty state of the art. The question was, why did he walk? And you have a paragraph here for exercise, Tesla walked between blah, blah, blah. And you can say, well, the answer is for exercise, right? Or exercise. And the model gets it right. You can see exercise here. The second question is about why did the university see a drop in applicants? There's a whole paragraph here, and you can see crime and poverty is the reason you see a drop in applicants. Now, the way triggers work here is you want to control the output. Or the adversary wants to control the output. So the adversary wants to put a different answer into the output. In fact, they may have a specific phrase that they always want to put in the output. So the trigger looks like this, where you have why, how, because as part of the trigger. That's what we find automatically. And then this underlying part, to kill American people, is a phrase that the adversary picks. You can pick whatever you want to, and that becomes the answer. So you can see model, why did he go for a walk? To kill American people. What is scary about these triggers is you can use the same phrase and the same answer on every kind of question. So you can take it another context here, and you can put exactly the same phrase here, and the answer in this case will also become to kill American people. somehow this trigger is making the model ignore everything, ignore the question, ignore the context. In fact, as high as a third of the answers become to kill American people. So we're able to get the model by adding this phrase to behave in this really undesirable manner. Okay. That was a quick run through the first piece of work. Now I'm going to talk about Sears. In this case, what we were interested in was making edits that keep the meaning the same. So again, we're taking X, we're doing some transformation, and this transformation is going to change a bunch of things, but it's going to keep the meaning the same. That's the main goal. Okay. And again, in this case also, we expect Y prime to be same as Y, because the model hasn't actually changed. Right? The input instance hasn't actually changed. You've just rephrased things. So an example of Sears is exactly what I showed you earlier. You have what type of road sign is shown. It says stop. You replace what with which, and it says do not enter. Now, very different from triggers, this is one where you could argue that this is an actual bug, and it is very likely in the real world. But this single example doesn't really tell you how likely it is. It just tells you that this happens for one instance. Is there a way to take this idea and generalize it? Does this happen for every question? Does it happen for certain styles of questions? Does it only edit? And so with the Sears stuff, we tried to characterize the scope of each of these edits by using some rules. And by rules, you should think of it as like regular expressions almost, or simple replacement rules. If you see this, then replace this, right? So for example, we would say things like, every time a question starts with what type, any question that starts with what type, if you replace it with which type, there are two things that happen. First, the meaning does not change when you replace what type with which type. This is sort of an automatic assumption that comes out of the model. And the second one is that the model changes its prediction a lot of times. And those are the sort of two things we're looking for. A different rule might be at an even higher level, where you can say, I'm not just going to focus on type, I'm also going to include just nouns. So if there is what noun, and I replace it with which, the same noun, the model changes quite a bit, but the meaning should not change. And in fact, that turns out to be the right rule, the right in the sense that it's the most broad one. It covers a bunch of questions, many more than what type, but also the probability that model changes its prediction is still pretty high. So here are some examples. I'll quickly go through some for sentiment analysis, which are movie reviews, and show you what some of these rules look like. These are very simple rules, but very surprising rules because they tend to affect the model. So here's the first rule. Movie is getting replaced by film. So what does this rule mean? This rule means that when movie is replaced by film, the model changes its prediction, even though it should not, because the review hasn't changed just because you replace movie with film. In fact, in this case, you can see the review. Yeah, the movie pretty much sucked. That's a negative review. You replace movie with film, it becomes a positive review according to the model. This is not movie making is negative, but this is not filmmaking is positive. Doesn't make sense. The model also gets affected by replacement in the different direction. So you can take film, replace with movie, and so you can have a review that's excellent film, that's positive, but you replace film with movie and it becomes negative. Okay. And there are a bunch of other rules that I encourage you to look at papers and look at it. Okay. But these are what I would say are actual bugs in the model, and we have automatically found those. There was no manual intervention here. You just let the system run on the data set, and it finds all of these examples. Okay. I quickly want to give you one last example before I talk about checklist, which is this example of slightly higher level intuitions of these transformations. In this case, we're going to be talking about implications. This applies only to question answering, so we're going to focus on that. And the transformation here is going to be to change the question such that you know what the answer should be. This is pretty vague. I'm going to give you an example and it'll become pretty clear. Okay. So let's look at this example. This is the visual question answering. You have an image here and you can ask how many birds are there? That's your X. Your Y is clearly in this, the Y is 1. Okay. How many birds? 1. Now, given this question answer, there are a couple of other things that get logically implied, like deterministic implied. For example, if I say, is there one bird? I'm sure all of you will agree. Well, if you have said how many birds? 1, then is there one bird has to be yes. Are there 2 birds? Well, no, because you said there were only 1 bird. And are there any birds? The answer would again be yes, right? Because you said how many birds? 1. In fact, these are such strong logical implications that you don't even need to look at the image to come up with these systems. These are question answer pairs, right? Conditioned on the fact that the model says how many birds is 1, the answer to all of these other questions should be deterministic. When you actually run the model gets the first answer correct. It says there is only 1 bird. Or if you say how many birds, it says 1. But for all of the other questions, it gets it wrong. Is there 1 bird? No. Are there 2 birds? Yes. Are there any birds? No. There's just no consistency in the model predictions. And so what we did in this paper is to create a huge data set for pretty much the biggest question answering data sets at the time, VQA and Squad. One was visual, one was sort of based on context, and automatically created these logical implications and tested the models at the time and showed that those models were not very good. Yeah. All right. So with that, I'd like to spend the rest of the time talking about checklist, which is the work we did last year. And the goal was to sort of bring together all of these ideas under a similar kind of framework. So the main goal here with checklist was to come up with a framework to help brainstorm and generate comprehensive tests for an NLP model for a given task. Right? Why did we want to do this? Well, at the time, there were a bunch of known issues that NLP models just faced, and many of those still is a problem. There are lots of shortcuts. There is a lack of fairness, and there is a lot of bias against specific people. There's a lack of consistency in the output. It's not robust to typos, things like that, right? And you've seen a bunch of examples of these, maybe all of these in this talk already. But the way people were approaching this was they would look at the specific issue in a specific task, right? So somebody would say shortcuts in machine translation, or not robustness to typos in question answering, or lack of consistency in NLI, right? And you can sort of do these pairwise things, and you can find papers out there, including our own. I'm not saying this is other people. But the tricky thing is, if you think about a user, the user has their own model and has their own task. And it's not clear from a point of the user for their model and their task, which of these is relevant. Like, are there shortcuts and biases on their own task? Like, there doesn't seem to be a clear way to know that. Are there other issues that are not one of these known ones that are kind of unique to the task that the user is looking at? Is there any way for the user to just evaluate the model, right? So we're going back to the main question. And one thing sort of that struck us was like, oh, if only we had experience testing complex systems. And turns out that outside of machine learning, this is a very common problem. People are thinking about testing complex systems, whether there are rockets or database systems or finance industry. Like, everybody's thinking about testing complex systems, specifically in software engineering. So are there lessons that we can use from software engineering to do testing better for NLP? Okay. So what I'm going to do is I'm going to outline some of the lessons from software engineering and how we can apply them to test NLP stuff. Some of these lessons will be common to you. Some of this, depending on how familiar you are, might be new to you. But their application to machine learning and to NLP is still kind of not quite there yet. So the first principle is to test small units, right? Create unit tests, test the small capabilities of your software. We don't really do this. And just to be clear, what I mean by small units is not like neurons or activations or attentions or anything like that. Those could be considered units inside the model. Instead, for NLP models, I'm talking about sort of the fundamental linguistic capabilities. Like, what do you expect the model to be able to do if you wanted to succeed on a task? And we'll see examples of this, but things like, can it handle negations? I should be able to write a unit test that just tests negations, or coreference, or lexical variability, and so on. Right? The second principle we looked at was whether we can decouple the test from the implementation itself. This is also really important, and actually for machine learning, it makes a lot of sense. You don't want to care about what the model architecture was, what the activations was, what's happening inside the network, the training loss, the optimization, none of that. If you're saying a model is able to do the task, you should be able to test just that functionality. So in machine learning or in NLP, what that means is you focus only on the test time prediction of the black box. Like explicitly treat the model as a complete black box, and you should be able to test whether it's able to do something or not. And the third thing we took from software engineering were the kinds of tests that we could use. The first ones were simple unit tests, where instead of just thinking of it as accuracy, what we were going to create were the set of minimal instances that are trying to test for a single capability. They're very simple, almost like sanity checks, but they're testing for a single capability. The second type of test that we're going to use is mutation testing, where we're going to take instances and change it somehow and see if the output changes or not with some expectation. And this is, of course, the stuff that I've been covering earlier in the talk so far. Okay. So I'll give you an example, and then we'll see if we have time to go for a different example. But let me give you this example first. So what we're going to do first is we're going to do sentiment analysis. So put yourself in the role of someone who needs a sentiment analysis system. You've been hired as the new machine learning engineer, and your bosses are telling you to create a sentiment analysis system. And also assume you're like an airline company, and you are on task to go to Twitter, find all the tweets, and classify that mention your airline and classify them as positive or negative. Right? Seems like a pretty practical use case. Turns out there's already existing models that companies sell. That is probably the one you should start with. So you would probably go with a big name like Google, and then that's the one that I'll give you an example of here. They have some model, you don't know what it does. You know that they publish papers and stuff, but there's some model that says that they can do sentiment analysis on social media. Okay, so now you want to test this system, right? Is it useful for what you want to do? The first thing you would do, or you should do, is to list the different capabilities that you think the model should have. If they're able to do the task, they should be able to handle these things. And we'll see examples of that. Then there are a bunch of tests that you have to make. So you're going to create sort of a matrix where you're going to put all of the tests as rows, or all of the types of tests as different columns, and the rows will be the different capabilities. Okay, I'll give you an example and it'll become much clearer. So let's look at the first kind of test that checklist introduces, which is minimal functionality test. You should think of it almost exactly as a unit test, where you're just creating simple instances that somehow are minimal in what they're trying to test. So we're creating a column for this minimal functionality test. And first, we are going to test whether the model is able to handle simple vocabulary that is required for sentiment analysis. Just like some words are positive, some words are negative, how good is the model in just handling that? So here's what we would do. We would write some simple instances like this was a great flight and expect it to be positive. I hate this airline, expect it to be negative. I like this seat, expect it to be positive, right? Create these bunch, send them to Google and see what the Google output is and just says pass or not. In some sense, this is accuracy over these just 3 instances, but the important thing is you've created these 3 instances just for a single capability. You just want to know whether the model understands great and hate and like, right? In fact, these 3 tests are not enough because these 3 tests are, they're very anecdotal. So Checklist has a way of generating hundreds or thousands of examples that follow the same structure. Very much like this was a great flight, but you'll create hundreds of examples of that. And then you can compute how good Google does or how good the sentiment classifier does on this whole set of test cases that are all measuring just a single thing. And turns out between positive and negative vocabulary, which looks like this, the model has a failure rate of 7%. So on something that's really, really simple, it should know what hate is bad, like is good, great is good. It still fails 7% of the time. That kind of sounds high to me, but again, depends on the use case. Right? Here's another example of a minimal functionality text. Maybe you care about neutral because a lot of people just say things on social media. Maybe they're not just having a sentiment towards your airlines. So you can create a bunch of neutral statements. You can just say declarative statements like, this was a commercial flight, or that was an English cabin crew, right? These are all handwritten examples. And you expect all of them to be neutral. And on these 2 examples, Google is wrong on one of them. And again, you can take these as structure. You can create hundreds and thousands of examples, and you can evaluate Google on all of them. And turns out 11% of the time, Google doesn't know that these declarative statements are neutral. And I'm not going to pick on Google. Let me just say the model that you're testing doesn't know 11% of the times that these statements are neutral. Right? So now it's not just about accuracy anymore. It's about specifically, how good the model is on neutral things, how good the model is on positive, negative, just with this simple structure. Right? But we go way beyond that. Here's another example of MFTs. These are unit tests, but we're going to target negation, right? So we're going to say something positive and put a not, or somehow negate the sentiment and see how good is the model at detecting negation. So here are a few examples. The cabin crew was not good is clearly negative. The pilot wasn't nice is negative. The flight wasn't great is negative. And turns out Google only gets one of them right. The other one, especially if the flight wasn't great, Google thinks is actually a positive sentiment. And again, we generate hundreds and maybe thousands of these kind of examples which follow the same negation structure. And turns out the failure rate is as high as 50%. These are very easy negations. All we've done is like added not in some way. And the model fails 50% of the time to get the right sentiment. Okay. That's just a single type of test. There are other types of tests as well. The second type of test we're going to look at are invariance tests. These are tests where you take an instance, and an actual instance. So in this case, you would take actual airlines tweets, and you would change something about them, expecting the output not to change, and then see how many times does the output actually change. Okay. So we're going to be looking at named entities first. These are just entities, or these are words that refer to real locations or real people and things like that. Here's an example. These are 2 tweets. The first one says, at American Air, thank you, we got on a different flight to Chicago. And the second one says, at Virgin America, I can't lose my luggage, I'm moving to Brazil soon. Okay. And what we're doing is we're changing these locations to a different location. So we're saying, let's replace Chicago, and it's a US city, to another US city, which is Dallas. Let's change Brazil, which is a country, to another country like Turkey. And what we are expecting, because of sentiment analysis, we are expecting that the sentiment wouldn't change. If you are positive about your flight to Chicago, there's no reason changing it to Dallas should change your sentiment. Same with the second one. You're moving to Brazil soon. I can't lose my luggage. Whatever the sentiment is, it shouldn't change just because you're moving to Turkey. Right? And turns out in both of these cases, the model actually fails. It changes. First one goes from positive to neutral. The second one goes from neutral to negative. And in fact, you can run it over a large collection of instances where you take real tweets and you change it and you see what happened. And when you're changing locations, about 20% of the time, the model changes its prediction. Just to be clear, we're not like just looking at, hey, does the probability change or something like that? We are actually looking at, does the model completely change its prediction? Okay. As the last type of test, we're going to talk about directional expectation test. These are tests where we are going to change the input again, as we've been doing, but have a certain expectation about the output to change. So I'll give you an example for the vocabulary, which we were trying to test whether the model knows positive and negative words and so on. And again, for directional, same as invariance, we are going to take actual tweets and we're going to change them somehow. The test that we did in this case was to take actual tweets, like at American Air, service wasn't great, and we added a negative phrase to it. You are lame. We added it to the tweet. In the second case, at JetBlue, why won't you help them? Oh, we added, I dread you, right? And the idea here is we are adding a negative phrase. There is no reason the sentiment should become more positive. If the sentiment becomes more positive when you add a negative phrase, you have failed the test. Right? And turns out, so the expectation here is for the sentiment to go down, or at least not to go up, right? When you look at this down arrow, you should think like it should not go up. And turns out in both of these cases, the model fails. And in fact, overall, almost like more than a third of the time, when you add a negative phrase, the model thinks the instance is more positive. Okay. All right. So what have we actually done with this checklist? These examples are fun to look at. It's always fun to show that these companies or these research models, the state-of-the-art stuff is broken, but what is sort of the actionable stuff here? What checklist provides is a paradigm and a tool to easily generate tests. What do you have to do? The first step of checklist is to look at your task, spend some time understanding what are the capabilities needed by the task. What are the different behaviors you expect it to have, right? If you're doing sentiment analysis, oh, it should know what's a positive word, what's a negative word. It should know negation. It should not care about locations, things like that, right? Then you should just write test cases for each of these capabilities, right? This is not specific to a model. You're just writing test cases and think about like different ways of defining this behavior and trying to write tests for it. Use label, unlabeled, synthetic examples, whatever you have in order to write these. And then the third step is the easiest one. Just run your model and you'll get a number. So you get a model is good at what the model is bad at. Yeah. Checklist also provides a bunch of tooling. I'm going to go quickly over what these do. We have a way to write templates. So you can start with a sentence like, this is a good book, and easily write a template manually that sort of takes that, this is a good book, and generates a bunch of other examples that have similar structure that should have the same sentiment, for example. We can also do things like automatically generate options. So we can say this is a good book and say, okay, what else can I put instead of good? And you can use BERT, which is sort of a state-of-the-art NLP model that will give you a bunch of choices that could go in there and make sense. And you can pick which of the ones you want to put to use to create test cases versus ones you don't. And there's a nice UI to be able to do this. You can also expand templates using lexicons. So we have lexicons of first names and last names, sort of differentiated by where they're from and race and sex and things like that. We have list of countries and nationalities and split by income and things like that. So you want to say things like, if I take a developing country and replace it with a developed country, does the sentiment change? Things like that. And same with US cities and religions and sexuality and adjectives, both for religions and sexuality and so on. Okay. We also use lexicons. We also combine BERT with WordNet. I'm not going to go into this too much, but there are clever ways to sort of figure out what are the right antonyms to replace as well. And doing it in a simpler way doesn't actually work. There are lots of perturbation functions like part of speech tags, contractions, rule-based heuristics, and so on. A lot of statistical expectation functions and things like that you might want to use when you're creating tests. Okay. All right. We also did some experiments to sort of show how well this kind of works. Give me a second here. Yeah, sorry, give me a second. Yeah, we ran 2 user studies, one with Microsoft people and one with some researchers. And essentially at Microsoft, they have a model that's very well tested. And they have their own benchmarks and things like that. They really care about sentiment analysis, so they have those people. And with question answering, we got some NLP researchers to sort of use this toolkit. And I guess to sort of let you know what the conclusions were, both groups felt that they tested capabilities better with checklists. They even tested new capabilities that they hadn't thought about before, even though they had been testing these things for a long time. And they found many new bugs. Okay. So just to wrap up my talk, I think we talked a lot about behavioral testing, perturbing and testing for a specific phenomena that seems really, really powerful. We talked about a bunch of automatic ways of doing this, bunch of manually defined ways of doing this, and you can look at the papers to learn more. And then we added with this checklist, which kind of tries to unify all this by providing a general framework and sort of a recipe on how to do testing for NLP. One thing I will do as the final takeaway slide is to encourage all of you to think about testing and making it as part of your pipeline, irrespective of what task you're doing. We've been talking to a few different NLP teams in machine translation, language models, and all of these tasks that we hadn't thought about. And for all of these conversations, the way they've gone has been an initial skepticism whether this stuff will even work, and maybe we were lucky in getting our tests or whatever it is. But people try it out, somehow get over the skepticism, try out. They usually are surprised by how problematic their model is, and then they tend to adopt checklist as part of their development. And if you are in the blue square right now, I would encourage you to at least try out some of these ideas, if not the tool itself, and hopefully surprise yourself and make your system better. With that, I'll thank you. I think I was a little bit over time. I apologize for that, but I'm happy to take a few questions if you still have time.
Yeah. Thanks, Samir. So it was very great talk. Actually, we have several questions, but unfortunately, we can take only one question. So maybe I can post one question, and the question is the following: that is there any notion?
And I can answer the other ones by typing them out. So
sure, that would be great. Yeah. So the question is the following: is there any notion of coverage of these tests that can be developed?
That is a really good question, actually. I think it's very, very difficult to do that, right? So the way that would be kind of nice if these tests were somehow comprehensive, but language is so difficult to sort of imagine what the space of language looks like, what somebody might ask. It's very difficult to determine. So yeah, in short, I don't have a good answer for that. What I would say is that these tests are designed to be red flags for your model. So just because a test passes, you shouldn't be like, hey, my model is perfect. The tests are designed to be more like, hey, if the test fails, you know it's a problem. If the test passes, you may not. And that exactly goes to the problem of comprehensiveness or coverage or any of these things. Yeah, it's kind of difficult, but diversity of tests is something definitely we are working on. Yeah. And maybe with models like GPT-3 and things, some of those things might be easier.
Yeah. Okay. Thanks, Samir, and thanks for accepting our invitation. Yeah, thank you very much.
Can I ask a question?
Yes, sure. Yeah.
Hi, Samir. This is Animesh here. So it was a fantastic talk. So I really enjoyed it from end to end. So as they say in modern day NLP. So I had one question, like the slide where you were showing these triggers about replacing film with I think it was like excellent film and excellent movie. So this kind of replacements. Yep. So I was just wondering, like whether the model in some sense was assuming that the phrase excellent movie is kind of a sarcasm. And that's why the prediction went the other way around. So I'm not sure.
That's a good possible hypothesis. It's not clear to me in that specific case. And it's also very difficult to know whether the model is doing it because of sarcasm or what it is, right? Especially if it's like it replaced credit to sarcasm. But yeah, it's possible something like that is happening. So when you're designing these tests, I guess you have to be careful about, would you call excellent movie a sarcastic statement? And I guess film and movie are so close to each other in my head that I don't really. It would have to be a little bit more explicit. Maybe the one with this is not movie making could be, this is not filmmaking, could be construed as sarcasm. I'm not sure.
Yeah,
but
sure.
Yeah.
So I was just wondering, like in the set of checklists that you developed, like these kind of test particles, if those could be also like a future interesting direction, like testing some sort of presence of simile, sarcasm, metaphors, and things like that. I was just wondering, like, if there is a scope for that.
I think that would be a great idea, and I guess whatever I've been playing around with these models, I expect them to fail horribly on all those kind of tests. They tend to be really bad at sarcasm, math similes, and metaphors and stuff like that. But it'll be fun to show for specific tasks. Yeah.
Thank you very much. Thanks, Samir, for attending the session and giving us like this great talk. Thank you.
Yeah, thank you for the invitation.
Yeah, thanks, Samir. Thank you. Yeah, so our next speaker is here, Professor Tim Baldwin. So we'll keep the bio short, but there is a lot of things to say about Professor Tim. And so Tim Baldwin is a Melbourne laureate professor in the School of Computing and Information Systems, the University of Melbourne, and the director of ARC Center for Cognitive Computing in Medical Technologies and vice president of Association of Computational Linguistics, ACL. His primary research focus is on NLP, including social media analytics, deep learning, and computational social science. So Tim completed his BSc and BA at the University of Melbourne in 1995 and M Engineering and PhD at the Tokyo Institute of Technology in 1998 and 2001. Prior to joining the University of Melbourne, he was a senior research engineer at the Center for the Study of Language and Information, Stanford University. His research has been funded by organizations including Australia Research Council, Google, Microsoft, Xerox, ByteDance, Seek, NTT, Fujitsu, and has been featured in MIT Tech Review, IEEE Spectrum, The Times, ABC News, The Age, Sydney Morning Herald, Australian Financial Review, and The Australian. So he is the author of over more than 400 peer-reviewed publications across diverse topics in NLP, AI, with over 17,000 citations and an H index of 61. So in addition to being an ARC fellow, and the recipient of a number of best paper awards at top conferences. So it's again a pleasure to invite Professor Tim and to speak in front of all of us. Thank you. Yeah, over to you, Tim. Thanks.
Great. Thank you for the kind introduction. Let me share my slides. If you can just confirm slides are visible, and we're actually,
Yeah,
so that should have the second slide now. We were having issues yesterday.
Yeah, all okay.
All okay. Excellent. Thank you. So it's a great pleasure to be able to join you in this fantastic event, IndoML.
It's not full screen.
It's not full screen. Okay, hang on. Try again. That should now be full screen.
No.
No. So what are you seeing?
No, we are seeing on the left side introduction, baselines, etc. also, and on the right side we are seeing create PDF.
Oh, how odd. Not sure why. Let me perhaps remove that. Odd that I can see it in full screen, but none of you can. Oh.
I think you have to put it into full screen mode.
Should have been doing that before. Is it workable as is, or?
Yeah, it's workable, but the right side is still seen. The left side has gone.
I'm not sure how to. I see. I can just drag this over. So I tend not to use this iMac for anything other than giving presentations. I'm not sure how to remove the right-hand bar.
So are you sharing the screen or you're sharing the application?
I thought I was sharing the screen, but let me try again. Oops. Okay, let's try this then to see if this is any better.
Yeah, this is perfect.
This is
okay. I don't quite understand why they didn't work, but excellent. We got it to work. Let me start again. So Tim Baldwin from the University of Melbourne, delight to be here. Cruelly scheduled alongside the first innings of the second Ashes test, I might note, but that's all right. As long as there aren't any comments in Q&A relating to wickets, we're good. Okay, so this talks all about fairness in NLP. Obviously, this is a very big topic nowadays, and I won't be able to do it true justice. This is very much centered on a series of papers that we've developed over the last 3 years or so. There are lots of references, if you go to those papers, to the broader literature. So forgive me for being slightly egocentric in how I'm presenting some of the work today. So when we talk about fairness, what sorts of things do we mean? Just to give us a taste of the topic for those who are unfamiliar. So in a broader AI context beyond NLP, real world examples, very recent real world examples would be starting out with Twitter's auto cropping algorithm. There'd been a lot of banter about whether it was biased or not. To Twitter's credit, they actually had a prize, a bounty for people who could expose biases in their auto cropping algorithm. They ran themselves back in August of this year. And the winner of that showed that indeed the auto cropping algorithm tended to select faces in images that were slimmer, younger, lighter colored skin with warmer tones. So obviously we've got an issue here in that it's going to select people of particular types and particular backgrounds and particular racial heritage, say, over others. So hence unfair in the sense that for no fault or no sensible reason other than the bias in the model, the autocropping algorithm is going to select particular individuals. So that would be in a vision context. In a sort of more general machine learning context, also earlier this year, back in August, there was an expose of automatic mortgage approval algorithms in the US, basically doing a manual version of counterfactuals, showing that if you provided the algorithms with basically all of the same features in terms of the person who was applying for a loan, with the exception of one critical feature, something like gender or their racial profile. So we've got the example here of white versus Latino, given this is the US context. You would have a flip in the label. So if the applicant were white, they got the mortgage approved. If they were Latino, they did not, despite the fact that all the rest of the details of the mortgage approval were identical. So, obviously significantly biased in terms of race and to a lesser extent other attributes. And again, inalienable properties of the individual, something that would legally be considered racial discrimination. One that's very close to home to me and was possibly the road to Damascus moment personally in terms of my own research was in the context of language identification, a topic that I've worked on and off over the years, where this is at Stanford, David Jurgens and colleagues at the time took a number of different language identification libraries, ours being langid.py in the blue there, and tested their recall. So basically sort of said, look, if we were using language identification libraries for health monitoring purposes, the way over Twitter, the way we would be doing it is by pulling out all of the English, in this particular case, tweets for different countries and running them through some system. So let's look at the recall of these different methods for English tweets across different countries and break down the results based on the Human Development Index of those different countries. And what you observe is this very confronting drop-off in recall based on the Human Development Index. So, a English variety like Nigerian English is going to be all the way over on the left here, whereas something like Australian English is going to be all the way on the right, which is a dreadful thing to think that a system that you have developed has as a bias. langid.py was developed well before people started systematically looking at fairness, but even so, it's going to perform a lot better for a certain category of population than for a different population. So to step back a bit, what is fairness in the context of NLP? So we tend to distinguish between source and target bias. So it's NLP, obviously, it all relates to text. And fairness tends to be in terms of, is it about the person who's written the text, so the source, or is it about the target, the person or the group about whom it is written? So if in this particular example, an excerpt from a movie review, if we read it, it's an adventure which reaches back to Golden Age Hollywood and the devil may care world of Douglas Fairbanks and Tyrone Power playing Zorro, or Errol Flynn playing Robin Hood. If I were to present you with that and ask you to predict what is the binary gender of the author, what is the country they are based in, what is the relative age of that person, you would probably predict that it's a male, more likely British than American, and probably an older male. And it's all sorts of subtle things. The devil may care, a very particular expression which would tend to be used by an older person. Or talking about golden age Hollywood, obviously someone who romances about a particular era of Hollywood, for example. And you'll be right. So this is written by someone called Peter Bradshaw, a Guardian movie reviewer who's about 59 at the moment and grew up in England. So there are lots of subtle signals in the text on the basis of the background of the author across all sorts of dimensions, which our models pick up on, and that leads to issues with fairness. I'm primarily going to be talking about source fairness, but just by way of mention, target fairness is something like, and this is taken from the GAP data set from Google. So we've got, it's a slightly confronting example. Eliza Bryant was born in North Carolina to Polly Simmons, a slave, and her master. So the task here is to disambiguate or do an AFA resolution over her, the pronoun her, as in, is it Polly Simmons we're talking about, or is it Eliza Bryant? The answer is Polly Simmons, and the point of the GAP data set is to expose the fact that co-reference resolvers and pronoun resolution systems tend to perform much better over male English pronouns than female English pronouns. But the point here is it's not about who wrote it, it's about the reference, the particular individuals who are mentioned in the text. Okay, so the sorts of protected attributes, as we will call them, of interest, so inalienable properties of the speaker, which are getting picked up on by our models and leading to these disparities in performance. It can be all sorts of things. So it could be something like gender. We'll tend to look at it as binary gender, more for machine learning convenience and availability of data rather than anything else. Race, which you tend to sort of get into very messy territory in terms of some of the nomenclature here, as in what is race? Is it more of a cultural thing than a genetic thing? And yes, there's all sorts of discussion to be had here. So we tend to follow whatever are national norms and acceptable labels in different contexts in terms of what does race actually mean. Age, in terms of ageism, although it tends to be reverse ageism, as we'll see, sexuality, all sorts of things. So it could be something like the interaction between hate speech and race, either source or target. It could be the interaction between the properties of the author, so age, gender, country, as we talked about with our movie review example, and ratings, say, and the ability of our models to predict the ratings for a product review or a movie review or whatever it's doing, or morphosyntactic analysis, or there are various contexts that people have looked at this in, either in terms of source or target fairness. Okay, so our primary focus today is going to be on algorithmic approaches. How do we mitigate bias? How do we train our models to be fairer? We're never going to make them perfectly fair, but we can at least hopefully do a better job through explicit training of different types. So, for those who are perhaps unfamiliar with the topic, a natural thing to ask in the first instance would be, well, surely if we don't expose any of the protected attributes to our models at training time, they're going to be fair, right? So this idea of fairness is blindness. What could possibly go wrong? And the answer is, well, for all sorts of reasons. In NLP, it could be because of the pre-training of our models and sort of baked in linguistic biases or sampling biases in terms of the data that our models have been pre-trained over. But it can be all sorts of things as well. What tends to happen is that our models would tend to pick up on these subtle biases and actually amplify them, so make them worse than they are in terms of label imbalances or imbalances in the distribution of protected attributes in the source data. So it tends not to work. It's a bad idea, or just sort of blindfolding yourself to the problem doesn't make it go away. Sort of a slightly more motivated approach might be to say, well, if it's a simple question of imbalance in the data set, there tends to be a little bit of a mentality perhaps of, well, the issue is with the data, it's not with my model. So if I can fix the data, the problem is solved, which is very often not the case. The problem is much more complex than that. But if we take that line, then if we balance our training data with respect to our protected attributes, surely that will lead to fairer models. So we're going to use this kind of cartoonish rendering of the setup of models with the box at the bottom representing our training data, where our predicted attributes here are going to be color to sort of try to pick a neutral context to talk about predicted attributes in. So if we have an overrepresentation of blue objects and underrepresentation of purple, we'll simply downsample the blue training instances so that we have balance between our purple and blue, and surely this is going to solve our problem. And the answer is no, for lots of reasons. So it tends to drive down overall performance, particularly when we have severe imbalance and underrepresentation of particular predicted attributes, because we're going to hobble our models in terms of the amount of training data that they have. But even so, it's not just that you get low accuracy but fair models, that the fairness still you tend not to achieve. So it's slightly better than perhaps fairness as blindness, a blindfolded first take, but not much better. Okay, so how can we do better than that? So I'm going to focus primarily for the purpose of this talk on adversarial methods, and I'll come back at the end to talk about a much broader range of methods that you could use. What we want to achieve is models which are as good as possible as at capturing whatever the concept that is associated with our target variable is, and as bad as possible at recovering whatever our predicted attribute or attributes, there can be more than one, are from whatever representations we're generating with our models. And the way that we're going to achieve that is through adversarial learning. Okay, so coming back to our cartoon representation, what we want to have is models which are good at predicting what are elephants and what are rhinos, but which are just hopeless at predicting the color. And we're going to explicitly use the protected attributes in our training data to train our models to try to achieve this. And ideally in such a way that we don't drive down the performance with respect to our target variable. Okay, so what does this look like? So the sort of simplest version of this is we have whatever base model, a transform or a CNN, whatever we choose it to be, or a simple logistic regression model. It can be anything at all. And we then have, we're predicting our target variable on the basis of whatever representations we're generating through our base model. And then we have one or more, depending on how many protected attributes we have, so one each, adversarial discriminators, which have the job of predicting relative to the hidden representation, the particular value for each of these protected attributes. So in our rhino and elephant example from before, we would have one of these predicting the color. Is it blue or is it purple? And the way that we train our model is via this minimax formulation. So we're trying to minimize our cross entropy as per usual. But at the same time, we're trying to maximize the cross entropy over our target variable, but maximize the cross entropy over our protected attributes. Okay, and we're going to have separate models for each of these two, but which are connected via the hidden representation. Both our base model and our adversarial discriminators are going to be back propagating, in the case of deep learning models, through the same hidden representation to achieve this. And in terms of training the models, it's not going to be differentiable as a minimax problem. So we're going to have an iterative approach where we fix our discriminators and minimize our cross entropy for the target variable, fix the parameters for the model there, then train our adversarial discriminators in terms of the maximization and repeat over some number of iterations until we get convergence in terms of our overall loss. Okay, so let's start out with that basic version of adversarial discrimination and test it out over a couple of different contexts, and we'll build on it variously as we pick up on some shortfalls in the basic formulation. So this is work from a couple of years ago now, 2018. So using this, and it's sort of showing its age a little bit because we're still playing around with BILSTMs, but in the first instance, we played around with the part-of-speech tagging task, where simple Google University part-of-speech tag set, so a relatively small number of tags. And our interest is, do we observe discrepancies in the accuracy of our model across particular predicted attributes? Okay, so we're going to in the first instance, train our model on sort of general domain text from the English Web Tree Bank. We're then going to further train it on a small amount of Trustpilot data because we have annotated data for predicted attributes in terms of the author attributes for Trustpilot, which we don't for the English Web Tree Bank, hence the two-step training. And then evaluate on Trustpilot in the first instance in domain. So Trustpilot is reviews of sites or brands, but also an out of domain or out of register, perhaps more appropriately, data set of African-American vernacular English. So from African-American populations in the US, completely different to our Trustpilot data. So partly to see, can we train fairer models in domain, but partly to see in training them to be fairer in domain, do we get crossover effects in quite different registers of the language? Okay, so for Trustpilot, we have age, as in user contributed age. People volunteer their age as part of writing a review on Trustpilot, or a subset of them will at least. So we binarize that, consistent with the earlier work of Dirk Hovey and Anders Sogard, and binary gender, male versus female. And we're going to look at accuracy in domain. So what we observe is, so the baseline without adversarial discrimination, just the pure BILSTM tagger, we observe the sort of characteristic discrepancy. So we get a fairly small delta in terms of binary gender and a larger delta in terms of age. So harking back to what I was saying before, we get this reverse ageism. Our models tend to do better on the text of older authors because that's what is overrepresented in the training data. Even for sites like Trustpilot. So this delta we want to bring down to as close to zero as possible for it to be a fair model. And indeed, when we do our adversarial discrimination, two things happen. So both the deltas come down, fairly close to zero, which is encouraging, but perhaps more encouragingly, the overall results go up. So we have both a fairer model and a more accurate model. What we find when we actually do analysis of the output of the model is the patterns in terms of the mistakes our models are making are much more subtle. The models are made to work a lot harder. They can't sort of fall back on sort of cheap heuristics in terms of, if it's a over 45 male who's using this particular term, then it's going to be a noun or a verb. It has to generalize, and in doing so, the errors are sort of much more all over the place, and there are fewer of them. Perhaps even more impressively, what happens when we apply the baseline versus the adversarially trained models, and bear in mind, they have no exposure at all to AAV data. So this is a completely held out register of data. So this is a little bit like the Lang ID case that we were talking about before, with different varieties of English from different countries. Say, where we're observing that our results are nowhere near what we get in the in-domain case, but over the different subgenres in this particular data set, our results have been lifted substantially. As I say, without any domain adaptation or doing anything specific for AAV data, simply through this adversarial discrimination, making our models fairer. So, very encouraging result to start out with. And over the task of sentiment analysis, so this is doing the Trustpilot 5-way, how many stars has the author assigned to this particular review based on the text. So again, showing its age slightly, a CNN now with an adversarial discriminator. No great surprises there. The extra predicted attribute of location, in addition to the 2 that we had before. And so it's balanced across the 5 countries. It's all English text, but from the US, UK, Germany, Denmark, and France. And what we observe is, once again, in terms of our F-score, bearing in mind this is a 5-way task, so that the numbers are quite a bit lower than what we had for the part of speech tagging, is our F-score for the baseline, as in without any adversarial discrimination, versus with adversarial discriminators trained on either individual predicted attributes, so just age or just binary gender or just location, or all 3, so with 3 separate adversarial discriminators. Our F-score either goes down a tiny bit or goes up a tiny bit. I wouldn't read too much into that. Here we're measuring leakage. So we had separate results for the delta similar to what we were doing before, but we're also looking at this question of leakage in terms of if I separate to my adversarial discriminators, train a discriminator on the basis of the hidden representation to predict the age or the gender or the location, say, how well would my model do relative to majority class? So, majority class performance, or the closer I get to that, the less information, the less demographic information I'm carrying across, meaning my adversarial discriminators are doing their job. So, we want these numbers to be as close as possible to the majority class numbers if we're truly bleaching out that information, which is largely what we see across the diagonal, age versus age, sex versus sex, location versus location. And with all 3, to some degree, we sort of do not quite optimally perhaps for the individual ones, but certainly across the board. We've removed a lot of the demographic information in doing this, and we've got similar sorts of results for the deltas. So, encouraging at this point, fairly simple architecture, but it seems to be very effective. So, kind of all rosy at this point. And there's a but. So when it works, it can work very well, but there are some caveats. And the major caveats with adversarial learning are instability, and related to that, the difficulty in getting the model to train sometimes, or its failure to converge. So what you tend to have is highly non-convex decision surfaces, and the model is getting stuck in all sorts of strange sinks at times, particularly for more complex models and more complex tasks, meaning it can be a little bit unpredictable whether when it works and it converges, it will tend to work well, but sometimes it just won't converge. So what do we do? So work from Yoav Goldberg and one of his students at the time, as a follow-up to our work, came up with a couple of sort of engineering solutions. So one obvious thing would be to add extra capacity to the adversarial discriminator so that it can do a better job, or upweight. If you were paying careful attention before, there was a weighting term, a lambda. In fact, there's one lambda for each of our adversarial discriminators for each of our predicted attributes. So if you upweight those, then they're going to have more impact and it will tend to converge better and perform better. Or you can ensemble them. And what they found in sort of doing a systematic analysis of this across different tasks was, these all sort of work to some degree sometimes, but there was sort of no one killer approach which sort of worked across the board. So there was, things were better, applying some of these engineering tricks, but still, yeah, this inconsistency remained. So this then leads into more recent work of ours from EACL at the start of this year, in terms of saying that, well, when we're ensembling our discriminators, so basically what we're doing is we have k discriminators instead of one discriminator per predicted attribute. And of course, you could have different numbers of discriminators for different protected attributes if you wanted to. There's nothing to insist that you have exactly the same number, but just to keep things simple. And we're going to, rather than just naively having an ensemble and kind of leaving it up to chance that our individual discriminators are going to capture different things and complement one another, we're going to add a constraint, in particular an orthogonality constraint on the parameters of the adversaries within a given ensemble. Okay, so for each of our predicted attributes, we're going to have this orthogonality constraint where we calculate the dot product between the respective hidden representations across the different adversaries, and calculate the squared Frobenius norm on the basis of that. Sorry, not the dot product, the inner product. One advantage that has been pointed out for this style of approach is it tends to both encourage the hidden representations to shrink to zero, but also discourage the model from just learning sort of rotated orthogonal representations from one another, which are sort of functionally equivalent to each other. Okay, so let's apply this and see if it helps in terms of both the performance, the relative fairness, as well as the consistency of our approach. So there are a couple of different experiments, but I'm going to focus here on sentiment analysis. It's a simple two-way sentiment analysis now on the basis of the Moji data set. Our predicted attribute here is going to be kind of raised in very heavy scare quotes in terms of African-American English versus Standard American English in the writing style. And we're going to look at, once again, this trade-off between the accuracy of the model and the gap in terms of the true positive rate and the true negative rate gap between the different values that we have for our predicted attributes. And here we're back to just one predicted attribute. The number will go up and down a little bit, as well as leakage, similar to what we did before. Okay, so jumping to the results, what we have here is the simple standard model based on the deep Moji pre-trained model in the blue versus a simple ensemble without any constraints in terms of the component models within the ensemble versus the differentiated ensemble with this orthogonality constraint. So what we observe is, in terms of raw accuracy, we're actually getting slightly higher performance, but importantly, lower standard deviation. So sort of more consistency in our models, which is good. Our gap is coming down substantially relative to the base model, and also much better, and again, much more consistent than the naive ensemble. And same number of parameters, same number of discriminators that we have in each case. So the numbers are directly comparable. The only thing we have is this orthogonality constraint. And leakage, much more muchness has come down ever so slightly. There's so much bias in the deep Moji pre-trained model that it's very hard to bleach much out of this particular model in terms of leakage. But in terms of gap between AAE and SAE, in terms of true positive rate and true negative rate, we're seeing substantial improvements. So that's good. So ensembling works, and ensemble, and we also had results for a single discriminator, which was worse again. Orthogonality definitely helps out. So again, all good, sort of sounds encouraging. The next thing we're going to think about is, okay, this is all sort of well and good if you have protected attributes for all of your training instances at training time. We don't need anything at test time in terms of inference, but at training time, we're, in our experiments up until now, we've been relying on having fully annotated data. What happens though in the sort of more real world setting where for some instances we have access to protected attributes and for others we don't, because of whether it's confidentiality issues or user disclosure. You know, some users have chosen to disclose protected attributes, others haven't. So we've got partially labeled data in terms of our predicted attributes. Can we still train these models? And the answer is, well, if you think about it, because we've decoupled the training of our adversarial discriminators and the base model, we can. You know, we can trivially just train the discriminators on the subset of instances where you have protected attribute labels. Easy. And if we think about it a little bit more, we can also pick up on the fact that we could transfer protected attributes from a completely independent data set if we so wanted. So we don't have to have any labels at all in terms of our predicted attributes. We only really rely on labels in terms of our target variable. But if we know there are particular predicted attributes with their potential sensitivities, we can potentially use data from an external domain for the training there. So let's start out with the case of the partial labeling in domain. So again, sentiment analysis. So what we have here in terms of plots is we're playing around with our lambda hyperparameter. We're comparing our accuracy versus our gap. So lower is better for gap, higher is better for accuracy, of course. And what we have with the different lines is we've either got 100% or 50% or 10% or 1% of the data, which is labeled with our predicted attribute. And what we see is, we get this intriguing result that the particular lambda based on the relative amount of labeling varies, we don't get much of a difference in terms of accuracy as we would expect, because the target labels are the same. It's only the protected attributes that have changed. But we can get very similar values in terms of our gap with a lot less data. And we can also look at this in an out-of-domain setting where we've got, instead of elephants and rhinos, so we know nothing about colors for our elephants and rhinos, we know about colors of whatever other random objects. And that's what we're going to train our adversarial discriminators over. When we do that using sentiment analysis task, but predicted attributes from a H-speech data set, we get the results that we see here, where the circles are in domain based on 1% of the data being labeled with protected attributes. The crosses are out of domain, so we certainly get a reduction and a higher gap for the same accuracy, but relative to the blue line here is the baseline of if I have just a uniform Bernoulli random variable, and I basically just randomly label my training instance with protected attributes, how would I do? I certainly do much better than that, and get what aren't completely useless results. So it works to some degree. Whether this is good enough for a particular application, of course, will depend on the specifics. So very small amounts of in-domain data go a long way. And fully decoupled training is certainly something you can do. You're going to take some sacrifice in terms of your target label accuracy just because of domain differences, but it can work, and we've got extra results in terms of trying to do sampling of the particular instances we use. I refer you to the paper for that. That was an ACL findings paper. So the last thing that I want to talk about, and we started a little bit late, so I assume it's okay to keep on going, but let me know if not, is intersectional bias. So what I mean by this is the way that we've trained our models to date is to say, okay, for a given group, so binary gender, for example, we have a single adversarial discriminator, which is doing in all of our examples to date, binary, it could be multi-class labeling of that particular attribute. So if we had two protected attributes, binary gender versus race, say, or color, we would have two separate adversarial discriminators, which are completely independent of one another, except the fact that they're both backpropping through the same hidden representation. But there's no sort of explicit structure that we're applying to those two. Where if we think about it, so that, that's the version of looking at our data in terms of the independent groups, looking at the individual rows and columns, or it can be a tensor, I guess, if we've got more than two protected attributes, but not at the interactions between them, where we can, of course, look at the intersectional groups, where we look at white males versus white females versus male people of color, etc. Where we're going to get, in the binary case at least, a lot more combinations as we add more and more protected attributes. So this is going to be the equivalent of sort of summing up the cardinality of each of our protected attributes. This is going to be the product of the cardinality of all of them. Or we can also go to what's called gerrymandering intersectional groups, where we look at the overlapping subsets defined by the intersections of all of our private attributes. So we have each of our rows and columns, but we also have each of our intersectional groups. So we end up with a slightly higher number again of combinations, because we sort of have the wildcard version that we throw into the mix. And we can use this insight either to simply represent our data. So we form groups over our data, and we can train our adversarial discriminators on the basis of these different groups. So gerrymandering groups versus intersectional groups versus independent groups, say. Or we could use it for evaluation. So we can look at gap with respect to these different groups. So up until now, we've only looked at gap with respect to independent groups. We can also look at gap with respect to our other groups here. The question here is, so when we evaluate, not just based on independent groups as we have up until now, but also intersectional and gerrymandering groups, how well do they perform? And if we do direct optimization in terms of intersectional and gerrymandering fairness, basically through this data partitioning trick by constructing these overlapping groups, how much of a gain do we get? And in the adversarial case, it's a simple extension. We just have more adversaries because we have more groups. I'm going to have to skip over the details. So there's a bias constrained model that we could think about here, where we have explicit constraints in terms of, based on whatever fairness criteria across each of our groups, we want the absolute difference between the performance for a particular group and the aggregate performance to be as small as possible, as in bounded by a slack variable, and use constraint optimization to train a model, but I'll have to skip over the details there. Just jumping to the results that we have here, what we observe, so this is now in the context of a biography data set, we're predicting the occupation, nurse versus surgeon in this particular case, with protected attributes of binary gender and economic status, we actually find, and there are details in terms of model selection that I would have to refer you to the paper for, but the red bars here are the bias model, as in simple, no fairness training at all. So our maximum gap in the worst case for a particular gerrymandered group is very bad. Whereas in our adversarial models, when we train them either based on the intersectional or the independent or the intersectional or the gerrymandered, so these three different versions of the groups, we actually don't get much of a difference. We get very small improvements in terms of average gap. Partly because of the trade-off between the complexity of the model. We have more and more adversarial discriminators against the expressiveness in terms of the different groups. The constraint-based model tends to do ever so slightly better, but it's a much more complex model and less versatile, shall we say. So again, adversarial methods have worked remarkably well, even without explicit training in terms of intersectional gerrymandering groups. They lead to improvements in terms of fairness with respect to gerrymandering groups, which is impressive. And there are extra results for other methods in the paper once again. Should I be finishing up at this point, or?
I guess yes.
Yes, that's fine. So let me just mention, and I'll share the slides, and you can look at the slides separately. So sort of big outstanding issues are model selection. It's hard, it's unsolved, it's leads to all sorts of issues in terms of comparability of results, as well as controlled experimental setups to be able to do careful analysis of under what data conditions do different models perform better or worse. Yeah, a lot of people use different data sets and, you know, hey presto, my model performs better, where perhaps, you know, under different data conditions, it wouldn't have performed anywhere near as well. And as I mentioned at the start, there are lots of other methods that we've been playing around with and others have played around with, but I will leave you to read about those in the slides. So just to summarize, we've talked about adversarial learning variously, starting out talking about how to achieve better stability through orthogonality constraints, then talking about the versatility in terms of partial labeling or complete lack of labeling of predicted attributes, and then talking about sort of gerrymandering and intersectional bias, and finding that, again, the adversarial technique is actually remarkably robust, even under that more expressive evaluation. And lots more to be done. And I just wanted to have a shout out to my wonderful co-authors, Trevor Cohen, Leah Froman, Shudong Hung, Yitong Li, and Shiva Subramanian, whose work has been presented here. And lots of references that I will leave you to read about in the slides. Done.
Yeah, thanks, Professor Tim. So we have one question from the attendees, and the question is the following: does the adversarial discrimination loss encourages high entropy over the protected classes, or it encourages the model to make a wrong prediction for the protected class?
It encourages them. It encourages high entropy. So it doesn't just sort of flip the labels. It encourages high uncertainty. So sorry, just going back. So we're trying to maximize our well, yeah. I mean, I guess strictly speaking, it's a bit of both. But we because we're maximizing cross entropy, we want it to be as bad as possible. So yes, I guess it is more the latter, making the wrong predictions.
Okay.
Could we model as a multitask learning problem? Yes, we could. It doesn't perform as well in our experiments.
Okay. Okay. So there is just one more from the same attendee. Could we model this as a multitask learning problem instead of an adversarial learning?
So as I say, we could, and we've got various experiments looking at that, but it tends not to perform as well as what we have here. And I mean, if you do it simplistically as a multitask learning problem, it tends to make models less fair. You have to have the gradient reversal trick that we're using here is a critical component of it. If it's just multitask learning, you're sensitizing the model even more to some of these differences. So you tend to get a rich gets richer effect.
Yeah. Okay, Professor Tim. So it was a pleasure to hear you here, and we are very thankful for you to accept our invitation. Thank you very much.
Thank you very much, and all the best to everyone.
Yeah, thank you. Thank you very much. Yeah. So our next speaker is here, Professor Abhigyan Chakrabarty. And so let me introduce Abhigyan. So Abhigyan Chakrabarty is an assistant professor at Indian Institute of Technology, IIT Delhi. His research interests fall under the broad theme of computing and society, covering the research areas of social computing, information retrieval, and fairness in ML. So prior to joining IIT Delhi, he spent 2.5 years at Max Planck Institute of Software Systems, Germany, as a postdoctoral researcher, and he obtained his PhD from IIT Kharagpur, where he was awarded Google India PhD Fellowship and Prime Minister's Fellowship for Postdoctoral Research. So prior to joining PhD, he spent 2 years at Microsoft Research, working in the area of mobile systems. So he has authored several papers in top-tier computer science conferences that include WWW, KDD, AAAI, AMAS, CSCW, ICWSM, and Mobicom. His research works have won Best Paper Awards at ASONAM 16 and Best Paper Award at ECIR 19. And he is one of the recipient of an internationally competitive research grant from Data Transparency Lab to advance his research on fairness and transparency in algorithmic systems. Yeah. So yeah, thanks, Abhigyan, and maybe you can take over. Thanks.
Yeah, thanks a lot, Mayank, for the kind introduction, and also for to all the organizers for inviting me to talk in this workshop. Let me try to share my screen. So just let me know whether it's visible.
Yes, it is visible. Yeah.
Okay. And am I audible properly?
Yeah. Yeah.
Oh, thanks. Yeah, good morning to everyone who is joining from India, and good afternoon or evening to others joining from other time zones. So in this talk, I'm going to present our work on fair partitioning of public resources, redrawing district boundary to minimize spatial inequality in school funding. I am a faculty member at IIT Delhi. I'm Abhigyan, and this is a joint work with Nuno Mota, Negar Mohammadi, Palash De, and Krishna Gummadi. So this work appeared in the web conference earlier this year. So in this talk, I'm going to focus on fairness in grouping. So most research works in fairness in machine learning, including the works you have heard today morning, they consider the groups which are socially salient. So that means that where the groups are formed by different users or different individuals' immutable sensitive attributes, such as groups based on gender, race, religion, and so on. However, in reality, a population is often grouped regardless of their sensitive attributes. So, for example, we divide the city residents into municipal wards. We don't look at like who is a we don't look at the gender or the race when determining this municipal wards, right? We group voters into electoral constituencies, or even in online platforms, we cluster a group users into different user clusters where the sensitive attributes may or may not have been used. Now, one important thing is that in such situations, people belonging to a particular group or cluster, they share the same fate. And this is an important thing. So your group membership determines how good or badly treated you are by the platform or by the entity, a particular entity. And this particular issue, that is fairness in group membership, it becomes even more pronounced when it considers the distribution of public good or resources. So in this talk, I'm going to focus on one specific instances of such cases, and this is about public school funding. So in the US, public schools are widely accessible and they offer tuition-free access to all the students belonging to different race, gender, different economic background, and so on. Now, these public schools are grouped into different school districts for better management, administrative purposes. And in fact, the funding for these public schools, they come mainly from the government sources. And there are like three kind of sources. I'll just talk about that in a moment. So the key question which we are interested in is how is the per student funding distributed across school districts, since our goal is to look at the fairness in distribution of this public funding or public good, right? So to answer these questions, we gather data on school district revenues, their strength, like how many students are there in different school districts, and school attendance zone boundaries. So every school has an attendance zone from which the students can enter the school. And we also look at the poverty level of the students as determined from how many students are can get like free lunch or reduced free lunch in the schools. In fact, to compare this data across different school districts in different states in the US, we also normalize this funding information using teacher wage index. So essentially, it gives us a way to compare school revenues or school funding across different states without caring too much about like what is the living wage or what is the living cost in those states, because that is being handled by this normalizing factor, which is the teacher wage index. Now, in fact, if we look at the school funding scenario, the government funding comes from like 3 different sources. So one is the federal source, that is what the federal government gives. Then there is another component from the state sources, and then from the local government sources. So this local government sources includes the like the city council, the local county government, and so on. So when we look at the federal and state government in the left-hand side, we can see that as the number of students from poor families increase in a school district, the federal and state government funding also increases proportionately. So in some sense, the federal and state government funding goes to schools where more poorer students study. However, when we look at the local government funding, it's exactly the opposite. So in fact, like more funding goes to schools where more wealthy people are there. And the main reason is that there is a correlation between the local government funding or the funding which the local government provides and the property taxes they can raise from people who are living in that area. So in areas where the property prices are high, those areas, typically wealthy neighborhoods, there the funding which the local schools get is much higher compared to schools where there is, schools in a poor neighborhoods. However, this particular funding source outweighs all other sources, and as a result, when we look at the total funding which goes into different schools, and in fact here we are talking about the total funding per students, we can see a clear correlation between the wealth and the funding different schools get. So in effect, the poorer students get much less funding compared to wealthy students. Now, in a different work, which was carried by a non-profit organization, EdBuild, which looked at also the racial aspects of the students, they found that non-white school districts get $23 billion less yearly than white districts, despite serving the same number of students. So there is a clear gap between the type of, between the amount of funding different school districts get based on either their financial conditions or even there is also a racial correlations to that. Now, the next question we were interested in is to look at how is the funding distributed within and across different states, how different states are doing. So if we look at this, so this is actually different box plots showing the range of funding which goes into different schools, different school districts. We can see that even when we compare the median funding, so and which is denoted by this red bars in all these box plots, we can see that in states like Alaska, New York, or Wyoming, the median funding per student is much higher compared to states in Alabama, Mississippi, North Carolina. So in these states, even the median funding which different school districts get is much lower than their counterparts in other states. And not only that, when we look at the range, that means the variance within different states, even that is quite high. So for example, in case of New Mexico and North Dakota, you can see the range. Like some school districts are funded quite highly and some school districts are funded quite poorly. Now, one important thing which we considered in this work is that, okay, we get that different school districts are funded differently and some school districts are funded well and some districts are not funded that well. But how far are these school districts from each other? Because if they're very far, it may not matter. But if they're close to each other, then it clearly shows us like a very stark contrast, right? So let's just look at one example. So this is a school district, Greenport Union Free School Districts in New York. Now this is surrounded by 3 other school districts: Sullivan West, Deposit Central, and Downsville Central School Districts. Now, if you look at the numbers which are shown in the parenthesis, so this is the per student funding this school districts get. And you can see clearly that while Greenport Union Free School Districts get only about $19,000 per student per year, its immediate neighbor Sullivan West Central School Districts, here the amount of funding, amount of per student funding is almost close to 60,000. So there is a clear and huge gap. And in fact, it's the same even in Deposit Central School Districts, where it is close to 37,000, and Downsville it's 30,000. So there is a clear difference between even neighboring districts. Now, here we touch upon an important concept in this inequality or the distribution being unequal. So if we look at, or if we try to understand the perceptions of inequality, that means like how people perceive these different inequalities, there has been some psychological studies which showed that people's perceptions of inequality actually depend on their social positions, as individuals typically do not observe the entire income distribution. So in fact, they often rely on cues from the local environment to guess the overall distributions of income, and then try to identify their place in those distributions. So in other words, let's say a person living in a village in India, that person may not care about how much Mukesh Ambani or Gautam Adani is earning, but they may care more if some people in the village are earning much more than what they can earn, right? So in some sense, the kind of envy or the kind of perceptions of how unequal different benefits are, it is manifested by their position and the local environment, like the place where they live, etc. So in this context, we propose a new notion of inequality, and which we call spatial inequality. So spatial inequality actually captures this inequality perception, where we compare the treatment among neighborhoods rather than we compare across the whole population and then say like which is more equal or unequal. In fact, in order to make this particular concept work, of this concept of spatial inequality, we need not have a specific geographical context, and it can be applied for various notions of neighborhood. So we can think about in an online setting, neighborhood means like people who share similar features or whose features are close to each other. But of course, like it has more direct application in cases where there is also a geographical neighborhood. Now, so let us try to define what is spatial inequality. So there has been a lot of works in inequality indices in the past, where people look at the income distribution in the population. So let's say that here I am showing like 6 different individuals and the amount of money they earn. One popular index is inequality index is known as Gini index, which essentially look at all individuals in the population and try to identify the difference between how much a particular person earns against the income of all others. And then there is a normalization factor. So essentially, we look at each individual user or each individual person and compare with all other persons and calculate the difference in income. And this we do for everyone. And then we kind of normalize to arrive at a particular index value. And the ideal setup is if the income is distributed, let's say if the government mandates that rich people should pay a lot more taxes, and this tax money directly goes into the account of the poorer people, then we would arrive at a situation where more or less everyone gets similar income or their earnings are the same, and that would lead to the lowest possible inequality. So that's the basic idea of inequality indices. Now, how is spatial inequality index different? So the difference is that instead of comparing between every individual in the society, we look at people's social network or social neighborhood. So essentially, let's say that this is the social network, like one person is connected to other people and it kind of forms a particular. So let's say that here is a cluster, here is another cluster, and we are just going to compare between these clusters rather than comparing with everyone. So essentially, we define spatial inequality index such that where, of course, we normalize with respect to all individuals in the population, but then within that, instead of comparing against everyone, we calculate the difference within neighborhood. So essentially, for this particular person, we only compare with like her income with the income of these two other individuals. Similarly, for this person, we compare with his neighbors, and we continue to do it to arrive at a number. And again, so if the neighborhood is dissimilar, it contributes more highly. And if there is again income transfer from wealthy people to not so wealthy people, then ultimately we'll arrive at a scenario where the neighborhoods are equal and the spatial inequality index is also quite low. Now we apply this idea of spatial inequality index to like our case of school funding. So let's assume that these are the different schools and they are connected based on their geographical proximity. So there is an edge. So we are basically forming a graph where the schools are the nodes and the edges denote whether two schools are close to each other. Now, as I mentioned, like for better management, we group these schools into different districts. So essentially, and these districts determine, so let's say here there are 4 school districts. So red, gray, blue, and purple. And different school districts get different amount of funding based on like what the governments provide, right? Like, so in this case, we can see that the red school district is much poorer compared to other school districts. So we apply this concept and we calculate the spatial inequality for different states. And again, we see that some states where there is very high spatial inequality. So for example, states like Colorado, Nevada, New Mexico, here there is very high spatial inequality. So in these states, there are school districts which are getting very low funding or less funding, and they are surrounded by school districts which get a lot more funding. And there are also states like Alabama or Vermont where the spatial inequality is lower. So there is a gradual spread from highly funded school districts to lowly funded school districts. Now, our idea is, can we redefine the school district boundaries? So what we have computed so far is on the existing school district boundaries, like whatever is there in the present scenario. But the whole idea is that, can we come up with a new district boundary so that the spatial inequality is lower? So going back to our example where we had this red school districts, gray school district, blue and purple. So this is the current existing school district boundaries. And what we are saying is that, can we redraw them? So by moving one school district from one school from one district to another district, so that ultimately when we look at the per student funding, almost all are equal. So essentially, when we compute the spatial inequality index over this new school district boundaries, it should be much lower than what it is originally. Now, as you can guess, like this particular problem maps to a graph partitioning problem in computer science. So essentially what we are saying is that we have different nodes and edges, and we want to partition the graph in a way that when we compare across different partitions, the average wealth or average property of that particular partition, it should be equal among the neighboring partitions. So that's basically the key computational problem which we are trying to solve. However, it turns out that this computational problem is an NP-hard problem. So in fact, it is NP-complete problem. So, so that means that directly minimize spatial inequality is computationally hard. So what we did in this work is we developed a greedy algorithm which starts from the existing grouping, although it can start from any arbitrary grouping, but in this particular context, we started from the existing district boundaries. We look at a particular neighborhood where the inequality is the highest, so which has the highest contribution to the overall inequality number. And we iteratively redistrict schools. So that means that we move one school from one district to another district to reduce the neighborhood inequality. And this we continue until we cannot improve the spatial inequality number, like we cannot lower the spatial inequality further. So this is a pretty standard approach, right? Nothing fancy here. But by applying this greedy algorithm, what we saw is that like we see dramatic decrease in spatial inequality number. So when we compare the before redistricting and after redistricting, we can see that across all the states, we have see huge improvement. The spatial inequality is much lower. So in fact, if we look at this effect on the district maps, so this is the map of Colorado before redistricting. So these are all the district boundaries which are current, and like different districts have different personal funding, and you can see that there are districts which are low funded, and they are surrounded by districts which are much highly funded than these districts. Now, when we look at the maps after redistricting, we can see that there is a kind of a gradual spread. So in all these cases, most of the districts are similarly funded, and in other extremes, I mean, they're more funded, but again, like there is no like island as such. So this is more homogeneous scenario. Now, of course, when we look at the variance in different states, again, like going back to this box plots, we can see the variance has decreased quite a bit, and this is expected because this is something which we also saw in the spatial inequality index values. But most importantly, the question is that while we are doing this, because this was our objective, that we wanted to redesign or redraw the school district boundaries so that the spatial inequality becomes lower. The question is that by this process, do we end up making school districts which are like either too big or too small? So when we look at the number of schools in a district, we can see that before redistricting and after redistricting, they are mostly unchanged. So we don't change the number of schools which in a district, and rather we move one school from one district, add it to another district, and maybe move some other school from that district to this first one. So essentially, by just transferring or exchanging schools between different districts, we could lower the spatial inequality index without changing the administrative overhead much. So because otherwise what would happen is that if we create very large districts, this would add to the administrative overhead. However, another important thing is that the policymakers may want to have a control to just limit how much change is permitted, right? So in this plot, what we are showing is that, like, suppose that there was a threshold that only this much amount of schools can be redistricted, like this can be either like 25%, 50%, and 75%, and so on. We are showing how much would be the reduction in spatial inequality. Now, there are states where we might need a substantial changes. So unless we move 50% schools, or we kind of change 50% schools from one district to another, we don't see much reduction. But once this 50% threshold is crossed, we see that we can achieve both 25%, 50%, 75%, in fact 100% of the achieved reductions in special inequality within this range. However, there are also states where we might need minimal change. So just by moving 25% of the schools between different districts in West Virginia, we can achieve very like high reduction in special inequality. And there are of course states like Nevada where if we can achieve something by just moving only a few schools, but in order to get the best possible outcome, we may have to move many schools. So there the policymakers can just set a threshold that, okay, we don't allow much movement, but we are happy with whatever reduction in special inequality we can get. Now, just to summarize, so in this work, what we did was we look at the spatial notion of inequality, like how different neighbors are equal or unequal to each other. And this captures people's perception of inequality because people don't really know the entire income distribution or like what kind of benefits different people are getting in a very large area, for example. And they may care more about their immediate neighborhood. Now, to capture this, we introduced a new special inequality index. We proposed a practical algorithm to lower special inequality in school funding. However, importantly, this particular concept and this kind of algorithms can be applied in other scenarios. We just have to change the definition of neighborhood, like from a special geographical neighborhood to online neighborhood and so on. Now, the question is that, especially coming back to the school funding inequality, we propose a solution which is computationally feasible, but can it be actually applied practically? Now that there are some questions marks there, because in order to redraw school districts, there needs to be a community participation, there needs to be legal changes and so on, like which might or might not be feasible depending on how how the political establishments are interested. If they want to minimize special inequality, it is doable, but it requires much engagement with the actual stakeholders. Now, just to briefly give you an idea of like where we can even take it from there. So if our goal is to counter the inequality in public school funding, another option is not to look at the redrawing the school district boundary. Let's say the school district boundaries are as it is, but can we bank on online educational charities? That can we ask people to donate more to schools which lack funding and which may be which may benefit from generous donations. Now, in these works, like which were I have listed the works, and you can go and just read this if you are interested. So we look at educational charities and see whether the online charities are actually helping reduce the inequality in school funding, and whether we can design different nudges to nudge users to donate more to poorer schools. And in fact, the ideas which we present in these papers are encouraging. And interestingly, one of the educational charities called Donors Choose, they have already implemented ideas similar to ours, which now clearly tries to incentivize users or donors to donate more to poorer schools. Now, with that note, I conclude, and I'll be happy to take any questions which you may have. Thanks.
Thanks, Abhigyan. So are there any questions from the panelists? Okay, great. So we have two questions from the attendees. The first question is there a threshold in terms of distance to denote close or not close?
Mm-hmm. Yeah, so in this case, we used a 5-mile threshold, but this is just an arbitrary number, so one can select the thresholds depending on the content.
Okay, yeah, so Professor Niloy, maybe you can go ahead.
Oh, thank you, Abhigyan, for the talk.
Yeah, thanks. Yeah.
So redistributing may have various administrative issues.
Right.
So some redistribution may be much more easier than others.
Yes, yes. So one thing is that like how much, as I mentioned, I think the main important thing here is the political goal, right? So one thing is like whether there is a push from the top towards achieving more equitable distribution. Now, in this case, it may require many changes in the lower level. Like you really need to change the school districts. Like although it doesn't require you to move the schools physically, but it needs a complete administrative overhaul. Some other cases, it might not be that difficult if it is just about distribution of money. Like at least how much money we can send directly to poor people, right? So right now the governments are more inclined to just offer monetary benefit across the board, as we are seeing this in the post-COVID scenario. But going forward, we may need more targeted distribution, that like people who are not earning enough, they should get most of the benefit rather just doing it across the board. So maybe that is something which might be a little bit more easily doable.
Yeah. Thank you.
Yeah, thank you.
So Abhigan, there is one more question from the attendee. So in the average funding versus percentage students graph that you have showed, so
this one.
Yeah, instead of looking funding as an absolute value, did you take a look at the value normalized with the total county spending or state federal GDP?
So we didn't look at the state federal GDP, but we tried to normalize based on the cost of living at that place. Yeah. So that was the idea, but this is interesting. I think we can also look at the percent of GDP which is being spent on different like schools.
Yes. Yeah, and then there is another question. So are school districts constrained by congressional districts? Like can one school district be in two congressional districts? And who controls the school district gerrymandering, like local, countries, or state level?
So this is currently done at a local level. So there is a local school district board which manages and which has representative from the local community members, as well as mainly this is from the city council, etc. But if there needs to be a change in the school district boundary, it has to be taken up at the state level, because sometimes one school district may actually cover multiple city councils and congressional districts and so on.
Okay, great. Yeah, so there is one, again, very interesting question. So what is the whole impact of this experiment? Like to advise the policy makers to fund uniformly?
Yes, I think this is a bit more computational policy work, I would say, and this is just to show to policymakers that it is computationally feasible to do such redistricting. Now, I mean, so sometimes what happens, let me tell you. So for example, in India, Niti Aayog publishes a lot of working papers. Now, sometimes what happens is that like the actual platforms which should adhere to this guidelines, they say that, okay, some things are computationally not feasible. So for example, there are a lot of e-commerce policies, and there is always a back and forth between e-commerce companies and the government, and the companies say that, okay, this is not practically feasible. So the kind of work we are trying to do, including this work, is like we are trying to propose policies which are computationally feasible to do or practically feasible to do, so that the government can say to platforms, in this case the government can tell the government itself that this is doable, but in, let's say, some other context, the government can tell the internet platforms that, okay, I mean, these are computationally doable, so why don't you take up this? So that is the broad level goal of this kind of works.
Okay, and what is the need of defining school districts here?
So school districts are needed because of better management. So the thing is that many things. So for example, teacher recruitment, or sometimes like purchasing different resources in bulk. Like if they want to purchase, let's say, tablets. I mean, so all this financial management and So basically, any administrative job is handled at the school district level.
Okay.
Instead of just letting it be handled by the local school management committee, like this are handled at a bit higher level. So that is why the school districts are needed. And that is the whole idea behind forming the school districts in the US.
Okay, and we have a last question. And it is like, can we introduce a temporal criteria as well as partitioning in addition to the spatial criteria?
This is interesting. We have not thought about it, but I think we should and we can. Yeah,
Okay.
Thanks for the question. Yeah, this is a very interesting idea.
Okay, and again, this question is from my side. What could be some interesting studies that we can do on Indian ecosystem? Very similar kind of studies, that one that you're describing now.
Right. I think so. One thing is that rather than schools, so right now here the focus was on education, but we can in fact look at, like, we have many districts, right? Like districts, and we can just look at like how different resources are being distributed across different districts within a state. So it can be, let's say, through the public distribution system, like ration, etc. Like, so it can be either based on like food grains or based on some other type of materials. One problem in India is that sometimes the data is not that readily available. But in case data is available which concerns this distribution of public goods, or at a government level how these distributions are being done, then this can be easily applied in the Indian scenario as well.
Okay.
Now, yeah, and of course, like so sometimes even in India, so there are also these concepts of like some districts are like real physical districts. So, for example, let's say like Delhi has 5 physical districts. But there are also sometimes conceptual districts, like they call it, like sometimes called police district, like where a physical district can be divided into 2 or 3 police districts for better management. So in fact, like for this particular idea to be applied, we don't need a physical district to be changed, like where it may involve a lot of cost, expenditure, etc. We can even look at a logical level, like when we have some logical districts, how we can better create this district so that the distribution is more fair.
Okay. Yeah, thanks, Abhigyan. So any other question? Any questions from the panelists? Okay, so we have no more questions. Thanks, Abhigyan, for this wonderful talk, and also thanks for accepting our invite.
So, no, thanks a lot for inviting me, and it was a pleasure talking to all of you.
Yes, so with this, we end our first session, and the next session starts at 4 p.m. today, and it is like ML in NLP, and we have 3 exciting talks there. Right, so that's all from our side. Thank you.
Thank you.